Alright, getting another stream started today. Most important part, of course, is the cat doing his cat thing over there in the chair. Currently, we're limited to camera angles that mostly involve the camera being a fixed distance off the floor. But this stream is about a project to fix that. It's a little bit pie in the sky, except imagine instead of a pie, a camera and a gimbal. Basically making a little robot that hovers around on cords, on winches, with a camera on a gimbal, much like a quadcopter, but without the spinning and the noise and the batteries and the running down and the wireless links. Sean in chat is giving me a hard time that it's supposed to be Gimbal. This is a psychological warfare campaign from chat. They're trying to implant a meme. It's not going to work. Anyway, welcome back, everyone. It's oh, we need a fresh SD card for the camera. Hey, Took. You are the cutest. Oh my gosh. You're the best little critter. Oh, can I grab the SD card or will the cat distract me forever? Oh, you jerked. Love you too. Oh my gosh, this cat is off the hook. See, this is why we need the camera. This cat's just so amazing. We gotta totally trim and show up his life, because clearly that's how we show our affection. I think he would appreciate having more people to play with, though. I mean, really, this is all rooted out of a desire to connect Tuco with more people on the internet. And, you know, just imagine how great it would be to have a dedicated stream where folks could follow my cat around and throw toys for him and, you know, project stuff on the ground for him to chase. You know, I think that would be fun. And it might take a few iterations of this hardware. Like, I think the first version of this will be largely manual, but I imagine that if I have, you know, especially if I set up like boundary zones, so, you know, you can fly around this part of the shop during these hours of the day, and I don't care what you do, and then other, you know, and then like conditionally I might have events that override that, and then I could just imagine this sort of semi-autonomous thing where my cat and people on the internet can play with each other. That's the dream, though, having a cyborg cat. I mean, if you can't be the cyborg cat, you might as well help your cat be a cyborg. Let's see here. I guess this one probably doesn't need formatting. That's interesting. So I have a new Python script that actually deletes the files after it pulls them off the card this time, so maybe I don't actually need to keep formatting it, but it seems like maybe good practice to help the file system avoid doing its usual thing where it has corruption that has no way of getting fixed unless you specifically look for it. I mean, this is all assuming that the actual flash is below some other wear leveling layer that's smart enough not to just let the repeated fat rewrites wear out the memory. Okay. Whoa. This is a great suggestion from Keithwana in chat, who says, OMG, make it so that the cats can play with each other over the internet. That would be pretty neat. Yeah, I think mostly the issue there is in, like, I don't know how successful it is controlling the manner in which my cat plays. So there seems to be particular things he likes, like fetching these bolts. But I have no control over these. All I can do is identify them and try to facilitate them. But if there is some way to proxy that such that, you know, whatever interaction my cat directed toward bolts somehow got matched up with another cat where that could then be connected with something that they would find interesting, like a combination of telepresence and a cat dating service, I guess. Tuco is dropping this bolt like he really wants me to throw it. I guess those are many of the applications for a flying cat seeking robot. There's a whole ecosystem of APIs to be built on top of this eventually, I'm sure. If it ever actually gets finished. I'm trying to keep this project within the bounds of something that I can actually finish in a reasonable amount of time. And that's partly why I want to make it somewhat extensible. Like, I'm planning on starting out with, well, I'm not going to say necessarily the simplest possible robot because I'm already thinking about adding a depth camera to it, which it didn't really need at first. But, you know, I want to avoid overcomplicating it too much at first, but plan to have, you know, easy add-ons. So basically leave myself places to bolt on accessories and have an onboard controller of some sort that has a reasonable amount of room for add-ons. And so it seems like the depth camera is probably the thing that's going to require the most onboard computing and I/O resources out of all the onboard stuff that I have planned. So I'll probably just try to find out what the minimum computer, or close to minimum computer is that will run that depth camera, and then use that as a guide for what to actually put on board the robot. And I suspect that's going to be at least a Raspberry Pi 2 or 3, maybe something that has USB 3 on it, depending on what the camera needs. I know there are some small computers now that have USB 3, but I haven't looked into which ones would be best for this yet. So then, I don't know, so that's one thing, is what computer to put on the robot. I got these new motors in the mail. These made a brief appearance on an unrelated stream earlier today when they arrived at my door. But let me get the other motors for comparison. All right, so this is my prototype spool so far. I was planning on using paracord, which, it's a lot of people use steel cord for this kind of a robot because it won't have much, if any, noticeable stretch, and it doesn't compress as you roll it up. Whereas this has both of those disadvantages, but it's a lot lighter weight, and I think it's also probably not going to. Like with the steel cord, that also really limits how flexible it can be on the spool. I'd have to use pretty thin gauge steel cord, but I still would probably need a wider spool for it to actually spool up nicely. So yeah, anyway, I mean, I haven't totally ruled out using metal cord, but it seemed, lighter and safer and nicer for various reasons to use paracord for this instead. And it also means that I can have it bend over a much tighter radius at the pulleys. It just generally seems nicer to work with. So I guess basically the little winch droids. Oh, I made a diagram. So this is simplified somewhat. The actual thing is going to be an actual three-dimensional object rather than a post-it note drawing, of course. But that also means I'm going to actually have 4 of these winches instead of 2. Do you want this, Tuco? I mean, 3 winches is the minimum you would need to have this move around in 3 dimensions, but I think I want 4 because, oh, you're playing with the cord. I see, yeah. So he does like to play with this stuff. I don't know if it would be any worse to have a wire that he would maybe want to play with and then like break his teeth on. Oh. Kaiwana in chat points out that also the O-droids, some of those have USB 3. That's cool. I'll have to check that out. Yeah, I have the O-droid U3 here, which I've used in some projects, but I think that's getting a little old now, and they probably have some new ones. So, yeah, he likes playing with these ends. Yeah. Anyway, so. Paracord, it's maybe not what I'm going to end up using as a final decision, but it's what's in the design right now. And the winch bots here, I've got 4 of them in this design, not because I need 4 to move it around in the degrees of freedom I need, but because that will let me fully cover the room. So if you imagine, let's get an overhead view. So that's my side view. And we also have an overhead view here. And the space here is roughly square. And so you imagine I pick 3 points here. So maybe I pick like this point and something over here. And so now there's no way to position the robot over here, because the position is always going to be, you draw a line. I mean, it's basically you inscribe a polygon with those endpoints, and that's the space that the robot can move around in. So, all this does is instead of having to have that vertex there, now I can have a vertex at each corner. And so there's some redundant movement, which means I'm going to have to make the control algorithm a little more general, but I don't think it's going to be that bad. I've been trying to think about the control in terms of layering a few different control loops, in terms of having something that can keep the cord moving at a controlled speed, and then something that can that can at a much slower pace try to regulate the tension on the cords, and then something that can try to regulate the well, I was going to say position, but at this level of the control loop, I actually want a fairly low-level notion of position that requires the fewest sensors to calculate as possible. So for that's where I've been thinking about using some combination of basically rangefinder sensors on the robot part. So, if you imagine the robot is like right here somewhere, and it's got winch cords going to each corner of the room. So then, Duco, what are you chewing on? Yourself? No, my anti-static cable. Don't do that, honey. You will be well grounded when you chew on it, but that's not really the point. So, the way I imagine this control algorithm working, so like first, this is again kind of at the lowest level where I don't have necessarily position control over the robot. I'm just thinking in terms of keeping it stable and safe and giving a good way of manually controlling it, and then assuming that whatever further automation is going to be layered on top of that. And then the, oh, that's interesting. P. Marin in chat says, it looks like the spider cam used in sports. Yeah, I've heard that these are used in sports. I didn't know what they were called, so that's helpful, thank you. I might have to research that. I suspect whatever professional version is way more money than I would want to pay for it, but it's also fun to design something like this from easily available parts and to fit exactly the space that I have. So yeah, I imagine having a somewhat manual control mode where I'm basically giving this thing commands that says, start out, baseline, just do whatever you need to stay stable and safe. But then on top of that, I want you to apply some tension to this winch cable. So then what I can do is, I'll have 2 joysticks on the controller. I can map one of them to the gimbal, pretty much like what I've already been demoing there. Then I can map the other joystick to combinations of those axes. So if, maybe I want to map that right arrow on the joystick to be, apply tension to both of these winches, and then just let the algorithm figure out what to do with the other axes to maintain stability. And so I think that would be a good starting point for at least developing algorithms that prevent all the failure modes I'd be interested in preventing. So, I want to make sure that the control loops in the motor, in the winch units themselves can handle, preventing motor stalls and making sure that the speeds don't get out of control and stuff like that. And they'll also be measuring the force on the cable using a little load cell. So, I'll want that to have some local smarts for, making sure that they, don't run into any failures that would require rapid attention. And then And then the Raspberry Pi is probably going to be responsible, or whatever computer is actually on here is going to be sending out like Ethernet frames to the controllers, telling them what to do with their motors, what forces to be aiming for, what PID loop parameters to be using, that kind of thing, and getting feedback in response. And then the algorithm on this robot controller would be figuring out, okay, I've got these requests to pull up tension in these winches to go that way, but then I'm also noticing that the overall tension in the system is getting high, so I want to try, I want to reduce, I want to bias everything lower. I'm also noticing that, I'm getting, too far away from the target, so I want to, bias in that direction. And I can try out different algorithms to see what would work best there. I haven't, simulated it or thought in a lot of detail, but I've just been trying to think about this enough to know, generally what hardware to put on the robot so that I can give it the sensing that it needs. Oh, Sean points out in chat that Skycam is the actual like trademarked name for this thing. So that's interesting. I'll have to check that out too. So yeah, I think that's basically what I want. So I'll have a couple of different levels of sensing. I'll have kind of a slow and relatively gentle control loop to try to maintain the right level of tension in the wires. But then I'll also have, and I think some of these control loops are going to be like tracking pretty tightly, whereas some of them will work more like, kind of limit switches, where if something gets, if the tension gets outside of a certain range, then I go into a different like tension regulating strategy, whereas otherwise I would let it be regulated by the other sensors. So then likewise, with distance sensors, I'm thinking I probably want at least 2 distance sensors on here. One sensor that we'll be dealing with here, a LIDAR sensor, and this is nice because it should be pretty accurate and fast update rate. And important for this, it should have a very narrow beam. Tuco, what are you getting into? Are you messing up a box of instructions? You're just being a cat. Okay. He likes it under there. So the LiDAR sensor, I think, might be a really good match for basically finding the focus range of the camera. So, the idea here is the camera has manual focus. I would be setting it to a fixed distance that's just whatever I want for photography's sake. And then the robot would be adjusting its position to maintain, roughly a fixed distance from the target I'm aiming at. So for that, I think this might actually be a really good match if I can fit this on the gimbal so that it tracks with the camera. So that's what I want to investigate in this stream. The other thing is I might want to just know generally how close this is to obstacles below it. So then, I would have another set of multiple control loops that have different amounts of kind of springiness to them. So there'd be a fairly tightly tracking control loop that would try to keep this right in focus using this LiDAR sensor. And that should be doable since this will give us a pretty accurate and quickly responding reading. We just want to smooth it for the sake of not having this thing jump around a lot for the sake of trying to keep in focus. And then I think for obstacles below it, I have a couple more of these sensors actually because I got them a while ago right after the Kickstarter when I thought they were cool and I wanted to use them for a different project that didn't really materialize. And so I might put another one of those on the bottom, but it might even be better to use an ultrasonic sensor for that because it has kind of a wider cone and just like if anything gets near it, I can kind of detect that and move away. So, so yeah, that's generally what I want. I think my next step here then is, so these other sensors, if I want a rangefinder, if I want a rangefinder pointing down, if I want one pointing up, if I want, if I want this depth camera, all of those are things that I can mount to the body of this robot and get approximately the performance I want. Something like the depth camera I might mount on another gimbal, but that seems a little excessive. I think I might just deal with it wobbling a little bit and try to fix that in software. But the gimbal is light, and I don't think I can put a lot on it, but it seems like I might be able to put the LIDAR sensor on it. So there are two problems. One is just like mechanically, is it going to be small enough and light enough to actually fit on here? I think the answer is yes, but we'll want to make sure. The other question is, how do I get data and power to this thing? I think that this has two modes, like a pulse width modulation mode where it just gives you a pulse that has a width proportional to the distance it's tracking, and that'll just run over one wire. Then it also has an I2C mode that's a little more flexible. I'm forgetting who told me this. Someone was telling me on Twitter that they've used these, and the earlier models, including the one I have, were kind of buggy over I2C. So for that reason, plus just to limit the number of wires I'm dealing with, I might just go ahead and choose the pulse width modulation mode, which limits some of my choices. Like I can't specifically trigger it, I can't change the triggering rate, but it keeps this simple. And that means that I just have to power it and get one wire out. And I could even do this wirelessly. I think the easiest thing to do would be to mount a little infrared blaster on here. So like a little LED and 555 timer or something that would take that PWM signal and just turn it into a modulated signal that I could pick up with one of those infrared remote control decoders. But that's even more complex than I'd really like. I think I'm just going to, I think after my time working on this gimbal, I think I would be comfortable putting one more tiny wire through there. I don't think that would overly constrain stuff. And I have some of this silicone insulated, really flexible 30 gauge wire that I think might do the trick. So I think that might be the thing to do, is just see if mechanically this will fit with the weight. I want to power this up and try it out, just make sure it works, make sure that the optical, I want to make sure that if I position it like this, for example, that the cone is so narrow that it's not going to be obscured by this lens, for example, or by the levers. And just generally kind of check it out. But then I think this will mostly just be measuring this in CAD or finding an existing CAD model, experimentally determining where the center of gravity needs to be for these components, and then updating my bracket model, printing another bracket, and then maybe while that's printing even, opening up the gimbal and adding yet another wire into the mess that we've already created. Oh, maybe we'll take a detour. There's a good suggestion in chat that, so I didn't know what these things were called. Apparently they're called sky cams, or at least that's the name someone made up that's starting to stick. And Don in chat is saying that you can search for DIY Skycam and find these, so maybe I will quickly do that and we can see what else is out there. I'd be surprised to find something that I can easily reuse for my circumstance, but it'd be interesting to see if there are some ideas we can borrow. Where's the mouse? This is the mouse, right in front of me. We don't need any of that. Oh yeah, some of these are even like designs that maybe they put stuff up on. So this is using continuous rotation servos, or is that just for rotation? Or is that for like spin, I mean? That looks like a Raspberry Pi camera with some pan tilt servos. Do they have any sample video from this thing? This looks nice, but I think we can do better. Yeah, and they're using Raspberry Pi and MJPEG Streamer. This is the same setup that I used to run the camera in the robot closet. And I mean, you've seen how reliable it is. It's all right, but it's not nearly as good as the stuff that's actually got a wire running directly into the streaming machine. What else do we got? This one from Hackaday. Is this just the camera mount adapter, or? Oh, so this is somebody who's already got a drawbot set up. I mean, I've obviously seen drawbots. They're really popular. And that's also something where, like, I know what they're going for, but the thing is, I don't necessarily care about absolute positioning like this with a stepper motor setup. I care about moving this thing around pretty quickly and then using feedback based on mostly the actual image I'm getting. So that's why I want, I need some amount of sensor feedback to handle the really quick stuff and the really safety critical stuff. But then past that, ideally I want something based on imaging running this thing, either a human in the loop driving it around or a computer tracking motion, tracking thermal image, correlating that to what this camera is seeing, something like that. Dr. Toon is suggesting, or a drone with a power cable hanging from the roof so it can fly 24/7. Yeah, I've certainly daydreamed about stuff like that too. I think my cat would freak out if I had that running. Not to mention I would go through a motor about every other day. Anything else we want to look at here? These are nice for inspiration, but so far I'm not necessarily seeing any ideas I want to pilfer. What's this one? This is on Adafruit. That looks nice. Oh, are those the motors they're using to move this around? Oh, they're selling a kit? Oh no, this is the motor shield. Anyway. And I thought about doing this with Raspberry Pi, Ethernet controller, motor shield, that kind of thing. That just if you're doing that for every single unit that's separate in, the corners of the room, that adds up to a lot of dollars for electronics that I don't necessarily need to spend. The solution I'm going with right now, I still have to buy motor controllers, but I can get those cheap from eBay. When I say motor controllers, I mean like an H-bridge on a chip, basically, which seems to be the easy way to drive these. Oh yeah, and then Ryan asks, how noisy are the motors? Probably less so than a drone. Yeah, lots. Actually, let me show you the motors I got. Unless there's anything else here to look at. Here's another Skycam from Reddit. Oh, is this the same one? Yeah, so this is just syndicated in a bunch of places. So this is using, are these NEMA 17 steppers or bigger steppers, something like that? These look like the little steppers that SparkFun sells. I have some of these. These are fun, but they're not very powerful, and I suspect that this would move very slowly and not very smoothly. And metal hardware and counterweights. So, and also, I forget who, but somebody was suggesting the strategy also of putting the motors at the top of the, at the ceiling and then having counterweights. But, let me show you the problem. So here I am at the desk. There's Tuco over there. And then any hardware I put up on the ceiling has to go way up there. I really hate climbing up there. It's terrifying. I really don't like doing it. So one of the goals with this project is to climb up there as little as possible to make this happen. So I think what that means is to have pulleys in the corners where the paracord runs from the robot up to the corners. How do I even point here? So the robot in the middle, then up to the corners, and then back down. And then I have the winch robot mounted somewhere that's out of the way, but at a convenient height for servicing it with no more than a stepladder. And then the power and data cable is going to be also kind of annoying, because that needs to go from the robot in the middle up to somewhere near the middle of the ceiling on a bungee arrangement, then over to the edge of the ceiling with some more tension, and then back down. So I think what that's actually going to mean is that I have pulleys, one in the middle, one somewhere else where it's convenient on the edge, that I can use to lower down the actual, the actual attachment points for those cables for servicing. So, you can actually see those two sandbag and pulleys right there. I'm not using those right now, but I put those up earlier for an art thing that I was doing. And I could either use, well, those aren't anchored very well. I'd want to re-anchor those if I was using those for this purpose. But something like that, basically, where I have an attachment point that I can usually keep near the ceiling, but I can lower down for servicing without having to climb up there. Okay, we have another request for making this a YouTube party. Oh yeah, and Kyle says, geez, you need someone to belay you. Yeah, basically. Actually, so you can see there's that orange ladder over there. I hate using that thing. It's terrible. It's an extension ladder, so it'll reach all the way to the ceiling, but it's heavy and terrible, and I can barely carry it myself. To get those hooks all the way up there for the sandbags, I have a friend who's actually kind of into heights, whereas I hate heights. And so she actually climbed up onto that roof truss from an area off to the left where it's actually kind of easy to get up there. And she climbed all the way across and just reached over there and attached the clamps and then climbed back. That was crazy. I didn't really want to watch, but it was kind of interesting. Is that seeing the lighthouse? Speaking of sensors, let me see if I can zoom in and look at the lighthouse. Oh yeah, you can definitely see the IR array there. This camera is explicitly designed to be fairly IR sensitive. I've also got some gunk on the lens, it looks like. Anyway, it doesn't need to be zoomed over there right now. Let me show you those motors. So yeah, those other projects were using a pretty lightweight motor, probably moving it fairly slowly and dealing with open loop and not losing any steps, kind of like a CNC machine. Whereas, sorry, I'm getting ahead of myself. I wanted to check out this one other YouTube suggestion. This was SpiderCam, SkyCam. All right. This one? Okay, great. This is a homemade kind of thing. Does this have audio? Oh, are those LMD 18200s? I used one of those to run a sewing machine off of a scooter motor a while ago. Okay, so this is also using cords instead of steel or wires. It's got a little bit of a problem with tension management, but it is using 4 cables. Or is it? Yeah, 4 cables. Nice. This is a little more bouncy than I would hope mine would be, but they're also starting and stopping the motors fairly abruptly, whereas I think I can ramp them up and down quite a bit nicer. Yeah, and they're getting into situations where some of the cables are getting entirely slack, which I would like to avoid. As much as I can by relying on feedback from the load cell, but also probably with some help from algorithms, just understanding how much cable should be taken up given the movement that's going on. Oh, is this going to be like a big one? Oh, I don't want an ad. Go away, ad. I don't want an ad in my video. Is this going to give me anything? You going to show me this thing working? That looks better. See, that's more like what I want, nice smooth motions. I suspect they're using much nicer motors than I have. They've got an e-stop button right there, which might be a nice feature to have on the ground. Yeah, it also looks like a nice heavy camera package. And theirs has like an attachment. I mean, I can stop playing this, but theirs had like an attachment at the top where all the wires came in, and then like a stalk kind of thing, and then the gimbal, probably with a weight in the middle for balancing. That's an interesting way to do it. I was imagining mine being more like a flat plate and then the gimbal, but that was largely because of convenience for mounting the electronics. That doesn't have to be how I do it. Yeah, Don also says in chat, there are a lot of college students doing this kind of project, including code. Yeah, I mean, I doubt I'm going to find anybody's college project with code that I actually want to borrow for this. I'm probably going to use this as an opportunity to learn Rust, if anything. Anyway, let's go back to, well, actually, yeah, I wanted to show you the motors. Let's open this back up. Okay, so there's the gimbal, there's the LIDAR sensor. Let's move this back slightly. So here is the spool that I designed so far. We may end up modifying this, but this is something that seems to be useful for testing so far. It printed in 2 pieces, super glued together. There's a shaft here that fits a 6mm D-shaped motor shaft for the set screw, which I've covered up with cord, but an M3 screw goes in there. And then a bearing in the middle that is actually centered on the spool there and fits an M3 shaft. So that's basically what's going on. It has a bunch of problems, which I've already enumerated on a sticky note here somewhere. The most obvious one at first is that the design is kind of mechanically over-constrained, where this hole should actually be a little bigger than it is, and then be constrained only by the bolt, whereas instead it's being constrained incorrectly by the plastic in some places, so that makes the whole thing wobble on the motor. Oh, Don mentions one important thing is that the cables must be connected to the center of mass so that as you move the gimbal, it will not swing. Yeah, that's a good point. I was planning on having the cables connected like at the corners with the center of mass like centered in the middle of that thing, but I'm going to have to be really careful about where I put the depth camera especially, and I might think about mounting strategies that make it easy to adjust it for center of mass, and or make it easy to add things to it without changing the center of mass significantly. So this is the motor I got at first. These things are all over eBay. I don't know what applications these are usually used for, but they're just basic worm gear motors that you see in a lot of hobby robot projects. They're pretty inexpensive. I think you can get them for like $10 or $12 each, which is not too bad for like a moderately powerful gear motor. I like them because they're worm gears. They come in a lot of different speeds. They're usually 12 volts. This one's the 200 RPM version, but it didn't have that much power, it turns out. Let's demo this. And I mean, I probably could have avoided ordering these either by finding better specifications from some eBay seller that actually had good torque numbers, and by calculating how much torque I actually needed, but a lot of it was I didn't really know what I needed at that point in the design. Plus, I was just excited about having some of these motors in the shop, because my shop, I have hardly any DC motors here. I have a handful of stepper motors just for messing around with, but I don't have DC motors, and so I just kind of wanted some for building little robot-y things. So even if they didn't work out for this project, I figured it would not go to waste at all. This is gonna flail paracord all over when I turn it on. Let's back this up slightly. Oh, the cat's got a good spot too. Let's see if I can get him on the camera. Under manual control this time. All right. Oh, cool. Kyle in chat has some useful terminology. Who says, when I did robotics, those little guys were usually called window motors, and their larger cousins were van door motors. That sounds about right. Yeah, and then Ben adds, yeah, I think they're usually for window blinds and that kind of stuff. That sounds about right. That sounds consistent with their power level. And I bet I could use these for similar stuff. Like, honestly, there are some windows in this place that could do with some automation. So maybe I could take a mechanism very similar to this. In fact, maybe even exactly this, since I don't think I'm going to end up using this for the real camera bot. Maybe I repurpose this to open and close windows in the shop. Although I'd probably want a different diameter for that. So yeah, this is going to make a mess of cord unrolling. So it's about the speed I want, I think. You know, max speed. And, you know, it's working all right so far. But it's pretty easy to stop this. So, okay, right now it's about, okay, 11.6 volts, about 12 volts at 100 milliamps. But then if I stall it out, stall current about 1.8 amps. But you can see that doesn't pull much at all. And in an earlier stream, I actually got out a luggage scale to measure how much this could lift. And, you know, it depends on the diameter, of course, but it was between like a half a kilogram and a kilogram best case. So not really quite gonna work out. It might work in a pinch, but it would be really underpowered and would probably make the whole project, you know, less awesome than it could be. So stop that. All right, so these motors I think I will save for a different project. And you also definitely notice the wobble. I think there are two things I'm going to have to do to address that wobble. One is, you know, as I was saying, redesign this shaft so that it's not over-constrained. The other is just plan for some amount of wobble and not have the sides of the chassis be overly close to this. So I'm just gonna have to account for that when I do the CAD. Although I think it's going to be less of a problem on this motor because it has a wider shaft. I think this is 8 millimeter. But yeah, this seems to be nice so far. I got a very heavy package in the mail today with, I think I ordered 5 of these to have 4 for this project plus a spare for something else and or making mistakes. These are rated to run at 24 volts, which is awesome. I don't have a 24 volt supply handy on my desk, so I'm just going to run this at 12 volts to demo, or at whatever this maxes out at. So you can see similar speed. This one's also rated at 200 RPM, whatever that means in terms of load, but like I cannot stop this one with my hands. I'm actually like afraid to clamp something onto this and turn it on because I think it might actually be powerful enough to do some serious damage. So this is pretty great. I think the next step for using this is to update my spool model and actually try this out to see how I like it, but I'm pretty confident this is going to do what I want. It's pretty burly. This is running at only 11.8 volts. What can I crank this to? That's at about 18 volts. Yeah, this motor is not messing around. 18 volts at 280 milliamps. You can see it's got like a nice big old shaft in the motor there with a big bearing. That's an exposed shaft spinning. So this is a much nicer motor than that little one. And it looks like a pretty nice sturdy gearbox. And so this one also, if I disconnect it, like there's no back driving this shaft. This is clearly a worm drive gear. So that's going to be what I want for holding this thing in place. Emily in chat is asking, is this a high-speed motor geared down? It totally is. In fact, I think I can demo that a little more clearly. I have some tape. Can we go into not so servo AF mode? All right, I'm gonna put one piece of tape on this shaft, and then I think I can get a small piece of tape to stick on the actual motor shaft as it appears on the actual motor. Let's see what I can do there. So yeah, that should give you a picture of what's going on. That unstuck from the shaft. But yeah, that motor's not messing around. I think these are going to be plenty. And so these are 24 volts. Means I can just have, I think I even have some little 24 volt, kind of like little metal box power supplies that might work for this. If not, I can find something similar. So yeah, and then just have a little buck converter to get all the electronics, probably 5 volts off of the 24 volts, and then they have their own local step down from 5 volts. So yeah, I'm happy with these. It's tempting to open this gearbox, although I feel like I'm probably going to get something out of alignment and or get grease all over my table. So if anybody really wants to see inside, I could open it, but I'm also happy to leave it unopened for the moment. I think I am excited to experiment with these LIDAR sensors next. Because, I mean, as fun as it would be to do CAD for that right now, like getting the updated spool printing, I think the next thing I want to print is the updated bracket for the gimbal. Like, I'd really like to get the gimbal done so that I can start building outward from that. And the only thing that I think I really want to still put on the gimbal is this LiDAR sensor. So we need to play with the LiDAR sensor. Oh, that's a great idea, actually, from Dawn in chat. It suggests turn the voltage down to 2 volts to look at the motor gear ratio. That's a great idea. Let's do that really quick. Put the little flags back on there. One little flag there. And one little flag there. And let's start this at the bottom of the supplies range, which is like 1.5 volts. Actually, does this go lower? I forgot the fine adjust knob. Oh yeah, that goes all the way to 0. Great. Just plug that in and ramp this up until it's just barely moving. Ooh, that's nice. That is 0.5 volts at 150 milliamps. Yeah, that's 0.6 volts. It's a pretty serious gear ratio. Can we count this? We need to find a reference point to measure this against. I think that's like a 30-to-1 ratio or so. I might have miscounted. Oh yeah, Emily in chat got the same result, about 30-to-1. And Sean, great, so confirmation. Cool. Yeah, that's a nice motor. I'm happy with my purchase. These were not as cheap as the other motors. I think they were like $35 each or something, which is more than I really wanted to spend for this project, but I couldn't find a cheaper solution in general, and I think these are going to be worth it. I mean, I think my value concept for motors is just a little distorted because of the market flooded with all these really cheap brushless motors. But the thing is, those just don't have a lot of material. It's just a little bit of copper, some machined aluminum, some cheap neodymium magnets, whereas this actually has a lot of machined metal in it. So I'm not going to be able to necessarily find something like this really on the cheap unless I pull it out of some equipment. And for that, I would just have to have some more patience in learning to find exactly what to salvage, whereas this, I could just find them on eBay made to roughly the specs I wanted. Oh, and then Ryan has another good question in chat. So is that speed obtainable through PWM, or how will they be driven? Yeah, I could definitely go down this low with PWM. So they will probably be driven using PWM with an H-bridge fed from a total voltage of like 24 volts. So I can max out the H-bridge at, you know, the motor's full speed, which we still haven't seen yet because my bench supply doesn't go up that high. But the motor drivers I have, the H-bridges are rated for, I think, 30 volts. So as long as the breakouts I got didn't cheap out on capacitors, that should be fine. And so there, I could definitely PWM it down this low. The danger is just with a DC motor, especially, when you start turning down the voltage, especially, you just don't have a lot of control over what speed you actually end up with, because effectively you can give the motor less power, but then it's really prone to get stuck, and as the load varies, the speed can vary quite profoundly. So just PWM won't necessarily let you run the motor this slow reliably, but PWM plus closed loop feedback will, and we're going to have closed loop feedback, not directly from the motors, but elsewhere in the design. So like this will be turning a wheel with the cord wrapped around it. And then, let's go back to servo AF. So this will be turning a wheel. Let me just stick this on here backwards for illustration. This is even bigger than the bearing shaft because the bearing is 6mm and this is, I think, 8mm. This would be roughly there, turning this, and then this would go through like a stabilization kind of pulley and then up to another pulley for measuring both force and, distance traveled. And so I think the way I'm going to do that is just with a pulley that's mounted on an arm. And so the arm will flex with a load cell to measure the force, and then the pulley will be mounted on an optical encoder that I'll use to measure the actual travel. And to keep the cord pushed against the pulley, I'll have another tiny roller that's on a spring so that I'm sure to get a good measurement of how much the cord's actually moving. So, oh yeah, so Don in chat adds that the PWM will let you get high torque with low speed. So yeah, you can do that really nicely with an electric motor if you have closed loop feedback. You just have to kind of know, it's like trying to press the gas just a little bit in a car. Like you can do it to move the car slowly. You just have to know how fast the car is moving for that strategy to work, or it's really easy to mess up. So yeah, and the other limitation here with the sensors, the encoder wheel I'll have here, that I can read just instantly, as soon as it ticks. I think the wheels I have on order, which still haven't got here, I think I got the slow shipping. Those, I think, are 300 counts per revolution. So I actually get updated pretty quickly as this thing moves around. And I can actually, I can make the pulley wheel actually pretty narrow also. So so it spins fast relative to the cord movement speed. So I'll have the ability to measure speed pretty fast and use that to close the control loop at that really short time scale. So over Ethernet, I can tell this thing, hey, start trying to take up the cord at this many millimeters per second, and it'll start trying to move the cord at that speed by PWMing the motor until it hits that particular optical encoder count rate. But then I'll probably have slower encoder loops or slower feedback loops for the load cell, just because load cells, since you're looking at a very tiny electrical signal, usually these kind of basic load cell amplifiers have a really slow update rate. I think this one might be much faster than like a regular digital scale, I think up into the like tens of hertz, but that's still slower to use than I want to use for that first tier motor control loop. Oh, interesting. Don in chat suggests that I should put the encoder on the motor shaft instead of the output shaft to get better accuracy. Well, I mean, doesn't that depend on what you're trying to measure? Because if I was trying to measure the motor shaft, then sure. But the thing I'm trying to measure is the cord travel rate, which changes, like the ratio between these two things changes depending on how much cord is on the wheel. So if I wanted to add a second encoder to the system, I could use an encoder on here to regulate the speed, and then have another control loop, try to figure out what the ratio is, and then use that at a higher level in the system. I guess I was just trying to avoid adding yet another encoder into the system, and it seemed like having an encoder on the cord would probably work pretty well. And Ben is in chat says, I would use an idler pulley on the cord. I think that's pretty much what I'm suggesting, isn't it? I think I've got a half-completed CAD diagram of this somewhere, but basically, let me use another sticky note since that strategy seems to be working. So, plan is big wheel here with hub about that diameter, gearbox shaft, motor, big ol' motor. Then, oh, this should be recording. Then I think what I wanted to do here was, I also care about center of gravity for this somewhat, because if I'm going to be mounting this on the wall, I don't want the center of gravity really far away from the wall if I can avoid it. So that's why I have the motor mass over here. So I'm assuming that the wall mounting bracket would attach somewhere around here. Floor mounting if I'm doing that, would be somewhere around there. So those are places where I might want mounts. Then I want the cord coming out actually further from the wall, because if the cord is right next to the wall, it's going to get stuck on stuff that I have near the wall. So just to keep the cord easy to not get tangled on stuff, I want it over here. So that means the final wheel that actually has the encoder will be over here. And it can be fairly small, but big enough to keep the cord on it. It'll have a little pinch roller that like idles against it. There will basically be a spring that holds these two together, and you would load the, I'd want like a lever that lets you open that to feed the cord through for loading it, and that would like clamp on there so that it keeps the cord against the pulley so that it can measure the distance accurately. And then this also would be attached, so that this axle is mounted directly to the encoder. Then the body of the encoder is attached to a load cell, which flexes as this force is exerted by the cord. So the cord comes up this way, goes off to the ceiling. And then, on the ceiling, it has another pulley that goes out this way. So then this side of the load cell is anchored to the housing that holds all the rest of the stuff. Then the cord, after passing through here, I want it then to go through another roller, which can also be pretty arbitrarily small. But this is just so that the angle of the cord entering this pulley stays constant, because otherwise I think it's going to affect the measurement of this load cell. So I want the cord on this side to be pulling parallel to the load cell axis so that it doesn't actually get measured by the load cell. So that's what this pulley is for. And then this pulley goes off to the whatever portion of the cord we're winding. So this angle is actually going to change as the bot goes up and down. So it'll either wind on to near the middle or near the outside. And so the ratio of this motor speed to this encoder speed changes actually by quite a lot as the bot moves around. But then this setup lets us, even as this angle changes, even as this ratio changes, this lets us continue to measure both this force on the cord and the amount of movement here. The force here also isn't going to be super useful as the bot is moving around dynamically, since it's not probably going to be fast enough to get accurate readings of the dynamic forces. So I'm probably going to be just smoothing that out and using that as a measurement of static forces to try to keep the cords from going slack and keep them balanced roughly. Oh, let's go to chat. I think there are some suggestions I'm missing out on. Oh, cool. Don likes my napkin sketch. That's nice. We got, was that the starting point? Is this the thing? Oh, thank you. That helps. That is opening up down here in Onshape. Whoa, this looks handy. It's, oh. So this seems stable, but I have two questions about this. First of all, where does the motor go? And second of all, how do you take it apart? Since that's a lot of what motivates the current design of the spool holder. And I haven't really talked about that much. It's not really that evident from this portion of the design that you're seeing, but basically the way this is intended to work is, the spool prints in two halves, the two halves assemble permanently, you don't have to take that apart. But everything around it does need to come apart, and it probably needs to come apart in two different ways. It needs to have like a disassemble for like heavy maintenance and or building it in the first place, where it bolts together in two halves probably. And then it also needs to have a hopefully easier procedure for actually just like loading and unloading the cord from the spool. So for that, I think I want the whole housing to bolt together in 2 halves, but then to also have enough of the top either open or with an access door so I can get in to load the cord, and to have enough access for that pulley. So that's another reason for, in this design, for having both of these pulleys at the top here, because I think if I design this right, I can leave the top portion of this somewhat open or having an access door so that I can reach in there and run the cord where it needs to go, but then leave the bottom of this pretty much fully encased. So then the other question I have, oops, that's the wrong thing. Yeah, the other question I have with this is, how does this bracket assemble? Like, is this one piece? And then this like slides in, and then you have to put this whole shaft through? Because if so, I don't see a spot for the motor. I also don't see how to integrate that into the same plastic piece as the overall housing, which means that this needs to be like a separate bracket, which I think increases the complexity of the overall design. So those are the questions I have about it, but like, it seems like there'd be ways to make it work. It just doesn't necessarily seem like the easiest thing to integrate in with the rest of the design that I currently have. But I appreciate the suggestion. Also, this spool is certainly wider than what I have. And the spool size was certainly a trade-off. I was trying to keep the spool pretty narrow so that I wouldn't need an additional winding mechanism to move the cord back and forth, so that I could just rely on the cord piling up and kind of creating enough of a narrow winding. That's also something where I wanted like a physical prototype to look at it. So like, if you just look at how this wound, that didn't really require any specific effort. Now, it maybe wasn't as controlled of an experiment as actually having it in a pulley before it winds, but it's consistent enough that I think it's fine. I do still worry about this jamming if, for example, I wind part of the spool with very little tension on the cord, and then go back and wind part of it with a lot of tension, then that part of the cord might slip under the other windings, which would create a tangle. So that might be bad. But as long as the weight of the robot is reasonably constant and I don't like have super jerky acceleration, I think I can avoid that. Oh yeah, so I guess this design comes from Gimbal29 in chat, who says, yeah, it's a quick mock-up. The motor would sit on the side and connect with either belts, gears, or an Oldham coupling, which I don't know what that is. That's curious. And then the things you mentioned definitely make it harder. Yeah, well, the other thing is I don't think I need a coupling necessarily. So like, okay, so gears. Gears, that sounds loud. Like if I could imagine having gear teeth actually printed into this and then having another gear here, which might be nice, but that seems like louder and clatterier than actually just mounting this directly on a nicely machined worm gear that already moves pretty smoothly. I guess I just don't see the problem with direct drive. Like the wobbliness was happening before, I think because I just over-constrained the shaft design. I don't think that was intrinsic to the design necessarily. So basically this would have its weight mostly supported by this bearing, by the center of mass, by an M6 bolt sticking out of the other side of the housing. And then this would effectively be turning the spool by the set screw. So if you can imagine it kind of being pinched between the curved part of this D and the set screw on the other side, and that little pinch is like a little vise that is then being turned by the motor as it's actually still on right now and turning. And so that actually I think would do a pretty good job of just, if I can get that basically between an edge and a point, then that would let me turn the spool without over-constraining it into a wobble. So I think that'll work. I'm not a mechanical engineer, but that's how I'm going to play my next move in pretending to be. Oh, Gimbal29 is saying that I should refresh and see the bearing snap in. Refresh. Oh, that's cute. And then you'd have like another piece that retains that, I assume. If I was going to do a gear or a belt drive, this might be a good strategy. I don't see how this makes sense, though, if I directly attach it to the motor. But, like, I could imagine something like this where, like, if I retaliate with a sticky note of my own. Oh, not that one, this one. Sticky note battle. So, for the purposes of quickly getting into this thing, I can imagine that well, I don't know. I was going to say something like perhaps the kind of skeleton of this device. Like, imagine you'd start out with this design, and then now imagine that the housing around it is basically occupying kind of that region, and then the spool fits in kind of right there, and then these other pulleys are kind of up here somewhat. I don't know exactly how these line up, but basically the encoder and idler and all that are attached to this support structure here. The motor could also be attached like near the bottom there if you wanted that. And then I could imagine this having a way for, if you wanted there to be a shaft all the way through, that could like pop out from the bottom. I just don't see any of that as being necessary. Like, so, I mean, I guess my vision for this was this piece stays, you know, as you're building this, I want most of this attached to one side half. I think that's just the easiest way to have this assemble and disassemble, is to make it two halves, have as much as possible attached to one of those halves, and have the other half basically be a fancy cover, and make the bottom half structural by whatever means I want. And for structural, like, I think the plastic is going to be fine. Like, I know this motor is burly, but like this is only printed with like my default infill settings. It's not even like designed to be super sturdy, and this is going to be not the weak link. Like, if I'm at risk of this spool breaking, then my robot is way too heavy. So like, that's not going to be an issue. And I think the way I designed this so that it's just one piece that balances everything on this center bearing, like, my goal there was to make something that was easy to avoid over constraining. So, and I totally messed that up with how I did this motor shaft, but I think in the other respect, where it's basically just sitting on one bearing here, I think that's going to be all right. The other alternative would be to have, you know, multiple bearings in there, but then I have to line them up, and I don't think I actually need the carrying capacity. And I'm not going to have any pull along this axis because there's another bearing or another pulley that's keeping the cord lined up right in the middle. So this only needs to be strong in this axis, and this bearing should do pretty much what I want. And so this bearing is then supported by an M6 bolt. Do I have one of those handy? Yeah. And I don't have this piece printed yet, but basically, so this conical recess here is room for a lot of material to support this bolt at being right there. So effectively the way this works is I designed this plate to hold the motor and any of the other like electronic-y doodads. It can do anything it needs to make that happen. Then this side can spend most of its strength at holding this really rigidly. And so it'll be supporting this with a lot of material right here and kind of fanning out into here. It'll have some thick bolts and pillars kind of attaching the two halves together. So basically, instead of that C-clamp shape from the CAD drawing from earlier, I'm going to be distributing that force across most of the perimeter of this whole thing. Since I only really need access along like maybe a 60-degree slot, maybe 90-degree slot, then I can use the rest of that for structural support and deal with not having to have a lot of pieces that individually have to be very strong. So like, this whole contraption is designed to be easy to remove. So this will be attached to the other piece with a set screw. Then this other piece will already have this bolt mounted. It'll kind of plug in, sit in there. Then I'll put some bolts in to hold that in. Then that's all there is to it. I could put this in separately, but then I'd have to have a captive nut back there, which I don't think would be a good use of the space. There isn't really space for an M6 nut between that and the motor shaft. Anyway, that's basically my design process, my design thinking for this work in progress. Oh yeah. So as Don points out in chat, so I'm using both this bearing and the gearbox bearing. So it is supported on 2 points. They're not just like at each side. I do have it skewed so that I'm trying to support more of the weight on this bearing. But yeah, the gearbox seems to have a pretty nice bearing in it anyway. So basically it'll, if you imagine that this was in there, I can't actually put it in because the shaft is not, the hole is too small right now. But if you imagine like these lined up roughly like I'm doing in the camera, then you have one bearing kind of over here, you have another bearing that's like right in the middle of this plane, and then that's being supported by this nut. So I think that's what's going on so far. And then Ben points out there shouldn't be too much side load on the bearing. I'm not sure what you mean by that this design shouldn't be too much, or that I should be careful not to put too much side load in general. Most of the load is going to be this cord pulling like this directly against the race of the ball bearing. So I think I've managed to line up the force pretty well, assuming this doesn't wobble a whole bunch as the motor's turning, but assuming I do a reasonably okay job at redesigning the hole and the set screw mechanism, that shouldn't be an issue. Oh, Gimbal29 in chat is going back to the box CAD, so I might have to go back there in a sec. I might go ahead and we can come back to the CAD, but I might already also start a thread on looking at the datasheet. The datasheet for this LIDAR sensor. We'll see what we have to do to get it active. Because I'm sure there's some information out there for the newer versions of this, but this is like the original version of this sensor that isn't sold anymore. So there probably are some differences, but this shows you how to wire it up in I2C mode. I think we want to be using PWM mode instead because it's supposedly less buggy and will involve fewer wires. Oh, so much CAD in chat. So US Water Rocket says, why not put 2 bearings on the spool and integrate a gear into the spool and put 1 on the motor? Then you have no load on the motor bearing. I think that's fine, but the gears will be loud and will have more backlash in them. And I think this shaft has such a big bearing in it that I'm not really worried about the small amount of load that this is going to put on it. I think the way this is designed, most of the load is going into my new bearing. Whatever load I'm putting on the motor, it's certainly got enough strength to handle in its bearing. If anything, I would have to worry about it wobbling, but I think if it does wobble, I would rather try to solve that problem with like a shaft coupler kind of solution. So if that's a problem, maybe my solution is I mount the bearing on the spool more rigidly than I'm planning on right now, so that it's actually like bolted through instead of just having the bolt stuck into it. But then I loosely couple that to the motor shaft instead. So then I use like maybe a plastic or a metal shaft coupler between this and the spool. So that's another option. But given that the spool is plastic, I think it might have enough compliance to not necessarily result in wobble if I design that right. Okay, so this is the sensor. You know what, before I even read the documentation, I'm going to take this apart. I think I can get into the back of this without opening the whole optics package. So, I don't really feel up to mucking around inside the lenses on this stream since I feel pretty sure I would just break it. But it looks like the back cover comes off and we could just look at the electronics, which seems fun. I think I have the right screwdriver handy somewhere. Man, this motor is just really silently humming along under with 0.6 volts on it. That's pretty nice. These motors were worth the money, I think. Well, I guess we'll see how reliable they are in practice, but at least for my little amount of playing with them so far, they seem pretty nice. I had a little screwdriver here. Oh. screwdrivers. Oh, these fit. Great. Oh, so just to be clear about the brand, so this is the pulsed light sensor, or the LIDAR light, sorry. Just to be clear, here's a bunch of gibberish nobody can parse. So the name of the company that makes this is Pulsed Light. Pulsed Light 3D, I didn't remember that. And then the name of the sensor is the LIDAR light, and their whole shtick is that it's supposed to be like a less expensive, lower power, more eye-safe, intrinsically safe kind of LiDAR sensor because of the way it uses a bunch of fancy digital signal processing and a lower power but interestingly shaped pulse of light. I think that's their whole deal. So they've had some newer versions of these sensors. This is the older version. I don't really know what the difference is. And that sticker is very shiny, but it's trying to tell us that this is a Class 1 laser product. So it's supposed to be eye-safe even if you're looking at it, although they don't really recommend it still. And I am going to be pointing this directly at whatever the camera is going to be looking at, but, we're not going to be gazing longingly into the camera for long periods of time, so I think a Class 1 laser product on it should be just fine. This is talking about meeting some FDA requirements. And then this is telling us that it's Pulsed Light Incorporated. LIDAR light, manufacture date, February 2015. Wow, so yeah, these aren't as old as I thought, and they've had 3 revisions since then, so I wonder what they've changed. Also, would be interesting to see what this is like without the little mounting ears, because I may or may not want that in Gimbal Town. I wonder if we can see the shape of the pulse on this thing. If I have any photodiodes, we can hook up to the O-scope and take a look at it. Ooh, nice. Anything interesting on there? Just a blank plastic cover. We'll keep those screws in place. Oh, that is so cute. So what is that chip? This might be time to go to the microscope. LCMX02. No idea what this is. I mean, it looks like it could be a system on chip or an image processing thing or an FPGA. I have no clue. I don't recognize a manufacturer marking on there either. It doesn't seem to have anything related to this Pulsed Light company on it. That says lard. Why does it say lard? Can I spudge this open, or is it soldered? It looks like it's just clipped on. Do I have a spudger that's in good enough shape? Oh, Dr. Toon has already identified this as a Lattice Mach X02 FPGA. Oh yeah, Lattice, I don't know what the CM is, but Lattice something or other Mach X02. So yeah, this is an FPGA. Great. And then a bunch of power supply looking doodads over here. I'm guessing these 2 pins here go to the photodiode, and this is some kind of really fast way to pulse the photodiode. And then this thing with the RF cage is probably their receiver. Oh, it's layered, not lard. I see. Let's see what's under the lard shield. As a vegetarian, I don't find lard especially appealing, but it's a funny word. Oh, that just comes right out. Great. That's not exactly what I wanted, but let's see what's under there. Whoa, this looks like I might break it. Help. Okay, that's like a grating. Wow. So maybe that's a filter? Because I would think that they would want the receiver to have a bandpass filter to get just the wavelengths they're interested in, so I'm assuming that's probably what that is. And then on the transmit side, they've got a long tube with a lens at the end. Probably a couple lenses. It's kind of hard to see in there. Nice. So that's the optics package, which I'm going to try to leave alone and not... Oh, geez, I just dropped the grating. Let's... Oh, I hope I don't break this thing. I do have a spare, a couple spares actually, but they're not cheap sensors, so it'd be nice to be able to use them all for something. Geez, I hope this isn't orientation sensitive. Okay, so maybe I keep this right side up. Okay, so let's not mess up the optics. Let's just leave that aside. Okay, what goodies await us on that side of the board? That is the burliest photo, or the burliest infrared LED. Wow, is that a laser diode? So it's mounted on the biggest heatsink lead frame I have seen in a long time, and it looks like it's emitting from the side of the die. This is probably an infrared laser diode. I've just never seen a laser diode in a through-hole package like this before. Oh, and then this is the feedback photodiode. Nice. So that's the laser or otherwise infrared photodiode. This is, what is that? That's another LED just pointing off to the side. Well, so I was going to say that this thing looks like a photodiode that they're using for feedback to regulate the power of their diode here. And that kind of makes sense where it's pointed. I don't know what this would be, though. That looks like another LED or another diode of some sort, but it's pointed even further off. Maybe there's like a... Maybe there are two different levels of power adjustment, like there's a kind of low sensitivity photodiode down here and then a high sensitivity diode that's further away from the emitter. That's the only explanation I can think of right away. But that explains why the driver on the back is a little bit complicated, so it's probably got the amplifier for both of those photodiodes. I assume those are photodiodes. That one definitely looks like some kind of photodiode amplifier op-amp kind of thing. Right below that. Below the actual burly high-power emitter thing, we have these, which are probably either MOSFETs or some kind of integrated driver chip. And then potentially more transistors that go with that contraption. Some of this might be just board-level power supply. Like this might be the board's LDO regulator. But this stuff is likely specific to the actual laser diode or infrared diode that we're dealing with. This is the capacitor that stores the energy that we're dumping out through that diode. Oh, Ben Brown asks if maybe those two diodes are detecting different frequencies. That does seem likely because of the different epoxies they're using. I don't know why they would need to detect two different frequencies given that the emitter is only presumably going to be emitting at one frequency, but maybe that's not right. Maybe this actually has multiple emitters in it. If this is actually a package with multiple laser diodes in it, that might explain it, but that would be a little weird. It also might be relevant that this is on the back side of the lead frame, whereas this one's on the front side. So maybe this one's going to be just intrinsically getting a lot more power off of the diode, whereas this one's more like just getting a little bit of power off the back side for some reason. Where does that go? Looks like those vias. Looks like it goes into this bottom six-legged chip there. I don't know that that's a photodiode. I think that might be an emitter. I don't know why they would have an emitter there, though. That is a weird place to put an LED. Unless that's just designed to be human visible somehow. Oh, there's some clues over here. Do you like clues? I like clues. Oh yeah. I think that might be an indicator or something. Oh, or it might be designed to illuminate the receiver. So maybe that's designed to be a synchronization pulse for the receiver or something. So if you look at the housing, is this a microscope job or a DSLR job? I think this is a DSLR job. Not that. Oh, I was getting those buttons confused. Okay. So in this housing that I'm already losing filters out of, you can see this little baffle around the emitter. So the emitter is mostly just getting a chance to aim right into that optics tube there with the lens. It's also got a path that allows that photodiode we were looking at to see the emitter. So if we match this up, so that's the orientation it's in. Then if we flip this around so we can see what's going on. So that matches up really nicely with the receiver. So that looks like it's just feedback to measure the power level of the emitter. But this transmitter seems to be pointing over here where it's either going to be, so I don't know whether the deal here is to, that's got to be why there's a cutout in the filter here. I bet that LED is illuminating the side of this optical element, whatever it is, and then some of that light ends up bouncing into the receiver. So my first guess for this is that that would be a feedback path that's used for timing synchronization. So that maybe what they do is they have like some, like, you know, and I haven't looked at any of the analog circuitry over there, but just kind of spitballing like what they might be doing to make this happen is if they're emitting like a really big pulse of light out of this infrared LED using some kind of circuit, maybe they actually have the same current dump circuit that just like discharges a capacitor into the LED. Maybe they actually have that same circuit wired up to both this big emitter and to this little side emitter thing. And then they're using this little optical side channel thing as a synchronization pulse for the emitter. So then it would see both this pulse and the phase delayed pulse after it reflects back off the object we're measuring. So that's my hypothesis so far about why that LED would exist. There's not much on this side of the board other than the sensors I was just distracted by, but there's this header here that looks like it could easily be UART or JTAG. That's probably for programming the FPGA. Maybe microscope time again. Oh, so Don in chat is saying, I bet it's a reference receiver. Air density / temperature will affect the time of flight. Yeah, okay, that's a great point. So yeah, so sync shouldn't be an issue because they can do that electronically. That is just measuring the propagation through the air as a reference. That's great. So in that case, we would expect them to be, you know, either periodically using that just to set the reference or kind of alternating pulses of that and the other sensor. Neat. That's a great hypothesis. Thank you. Okay, so we've also got this little 3-pin bugger. That might be something to drive the outputs on this cable. I haven't really looked into that. Yeah, so that's the thing that's probably a debug interface. Can we see where that goes on the other side? I might put this back down just to cover up the optics since there isn't much else we can see here. There's the photodiode. This is a nice little assembly. I wonder how hackable it would be with other FPGA designs. Oh, so there's, that would also look like JTAG, wouldn't it? Yeah, I doubt these are both JTAG. This might be some kind of debug interface that they made with whatever signals they wanted broken out. So there's ground right there. That might be power. Where do the other ones go? Goes to like a ferrite beater, resistor there, some other stuff. Kind of hard to tell where those go. They're probably using an internal layer to get to the FPGA if they are JTAG. They might both be JTAG. It might be one for like developers and one for factory test. That looks like Lattice's little pluggy thing. I forget what it's called, but I think that's a common interface. Oh, okay. So Don is saying the change in attenuation based on temperature is what they're probably measuring. And Dr. Toon is saying that this is a 1 watt, 905 nanometer laser diode. And they assume it's only class 1 due to the very short duty cycle. Yeah, that sounds about right. Yeah, a 1 watt laser. So that's the capacitor with all that energy. So yeah, I think that's some Lattice interface. I think that might just be redundant or with some other debug signals that they wanted for testing. Let's see if we can non-destructively open this shield. Spudger. Do us a spudge, little spudger. There's our diode mounted all fancy-like upside down. I'm sure that's a really sensitive amplifier they've got going. Someone who's more of an analog guru could probably also tell me exactly what this circuit is. I mean, the usual thing that you use for a laser diode like this, or not a laser diode, a photodiode is a transimpedance amplifier for the first stage, and then another gain stage with some kind of filtering based on your application. So yeah, I'm not going to go really deep into this analog stuff, partly because these things are even difficult to identify. Let's see if we can get at least some of this. That one looks like R9S, ALS, another ALS, and then a G00 in a big old 6-pin package. So this is probably just their amplify and filtering stage, although the manner in which they're doing the filtering here is probably actually pretty important to the application. We might take a closer look at this, but I think the next step might be to turn it on and at least, watch it work and maybe probe around a little bit. Let's put this back on for the moment. This is pretty easy to get on and off. Oh yeah, so the data sheet, which we haven't looked at, I actually want to look at that. Maybe we should do that next. So Dr. Toon says, the data sheet says that standard detector is based on a silicon pin diode, but optionally could support a silicon avalanche photodiode for greater sensitivity and range. That sounds fun. I get the feeling that a lot of what they're doing here is pretty inexpensive hardware combined with fancy signal processing, but we might find some interesting tidbits in the hardware too if we look closer. Let's dig up the data sheet from this original thing. Let's be using the computer, I think. I think I saw this on SparkFun. I don't know if it'll be called the V1, but yeah. So SparkFun still has a page for the original one. I think I even ordered this from SparkFun, actually. So this is actually literally the one that I have right now. Oh yeah, it's right here. Edge emitting, which we just saw. We just saw it actually mounted on the edge. 905 nanometer, 1 watt. Yeah, and a surface mount pin diode. 3-degree FOV. 5 volts, 100 milliamps. Cool. Yeah. However, operating the sensor without its optics or housing or making modifications to the housing can result in direct exposure to laser radiation. Yeah, that seems bad. We would not want to do that. So having the back cover on while I operate this is probably a good idea too, even though it seems like that's pretty well baffled. But that would hold it into place nicely. Under no circumstances should you ever stare straight into the emitter. Probably a good idea. So there's the module there in the corner. Scope is on screen because we're going to be using that shortly. Yeah, short bursts. A novel current driver with a nanosecond signal transitions, which probably means that they used fancier MOSFETs than the folks who tried this before them had available to them. A signal processing approach is implemented in a single programmable logic chip. Hey guys, we know how to use FPGAs. We thought we'd put it in our data sheet because the marketing needs more bullet points. Hey guys, we put multiple things on an FPGA. Throw it in the bullet list. Alright. I think I can just get a PWM signal out of this without having to send it any commands or anything. Does this even have the pinout? Why would this not have the pinout? What possible reason would the datasheet have to not have the pinout? Here's the tech brief, which has some more info about time of flight. Also not useful. I assume their GitHub info, their GitHub page has some. This site doesn't exist anymore. LidarLight.com is no longer a thing. Great. Well, actually, that's interesting. This has the wiring diagram for I2C, which mentions a mode pin but not a PWM pin. I assume that you need to like tie something to something and then the PWM starts coming out. Let's see if this diagram they claim exists for PWM is actually still available on GitHub. Just why would they not put that in the datasheet? That's what datasheets are for. Let's see. Oh geez, they have a separate thing for technical stuff. This seems to be marketed toward the technically curious, but in fact, this is just the basic stuff that you would need to use this module at all. Let's see if that website still exists, and then head to GitHub. Of course not. Why do people make URLs that don't last? I mean, there are all sorts of reasons, but a lot of them are bad. I guess this company probably got bought up. I think Garmin makes the new versions of this module now. I also just hate the way the whole startup machine works, where people have great ideas and then their end goal, like the best thing that could happen, is some giant company buys them and just destroys half of everything they built. Anyway, we can turn the cynicism dial down slightly. Is this still in existence? Documentation. How much of this is still relevant to the old version I have, I wonder? Oh, great. I think this is what I want. LiDAR Light V1 docs. Oh, silver label. So they noticed that too. Yeah, it's like impossible to photograph. It's so shiny. Great. I want to save this in case this disappears. Can I just clone this repo? Let's fork this. Oh, I'm not logged in on this machine. Let's just clone this repo for now. I don't really want to be logged in on this machine if I don't have to. Get cloner. Put it in the cloner mat. Well, I think if I do go poking around in this, I want to make sure that I can like stick it down solidly into this housing. It looks like if I put this down in there all the way, there's a pretty nice solid baffle around the actual diode. I just don't want this coming up while I'm using it, so I'm just going to tape it down. Kapton tape will save my eyesight. Cool, so that should be safe to operate. Don't take my word for it, kids, but I'll trust it for myself at least. So then does this still have room to plug in with my crappy tape job? It kind of does. They did at least give you a red wire for 5 volts to try to tempt you into not plugging it in backwards, which is kind of nice of them. I guess they didn't want a bunch of negative feedback that people just blew up their module without getting to test it at all. So 5 volts here, ground on the other side. Then we just need to figure out how to wire everything else to get PWM output, which I'm sure we could just do by trial and error, but I think this documentation will also tell us what we need. Wow, the V2 docks are way bigger. I'm assuming they either added more features or used a different typesetting package. Actually, I'm curious to open both of these. This is the blue label version. Ooh, the blue label. Oh, this has more drawings. Oh, this is nice. They save you from opening it. Oh, and there's another jumper here. So this explains what that is. Is that just a copy of J1 or? Oh, neat. So there's primary interface. This, I mean, and this may not apply to the one I have. I'm looking at the other version first, but. So that's the primary interface. Oh, and here they're saying the mode pin doubles as the PWM output. That's interesting. And then the secondary header. Ooh. There's a separate power input that you can use to power the laser. There's another regular power input for everything else. External reference clock. Interesting. So this is definitely separate stuff that's not the regular port or JTAG, but it is hacker friendly. That's nice. Got some power supplies. Ooh, drawings. Let's see if the V1 docs are anywhere near as good. Oh, a block diagram. This is nice. So they tell us what's going on in their FPGA and in their analog. Oh yeah, and they even talk about the reference transmitter here, so that's what we were seeing. So 2 little amplifiers with 2 different diodes, a local loopback path, analog filtering, comparator, and then all this stuff is in that Lattice FPGA. They give out a little system on chip to implement their buggy I2C. Cool. This is their secret sauce because they put it on an FPGA and didn't release the source code. That makes it secret sauce. 50 megahertz. 4 nanosecond edges. That's nice. Yeah, so these newer documents might not directly refer to the one I have, but they definitely seem to be more thorough. Ooh, yeah, the avalanche photodiode needs this external bias voltage that they let you supply externally, I guess. Let's get not too invested in this document since this isn't actually the one I have. But I2C, PWM wiring. Oh, this is basically what we want. Ground, power. Oh. So here they're using this mode pin bidirectionally. Oh, that's great. So I don't have to give up triggering. This works kind of like the parallax ping sensors where they use one bidirectional pin to trigger the sonar pulse going out and then to read the distance. So that's great. That gives me the functionality I want. Doesn't have me relying on a potentially buggy I2C and lets me just use a single wire. So yay. I think that's what I want. Okay, let's take a quick look at the other document just to see if there are important differences. But I think we've got the info we want. So this is the silver label with its slightly less posh looking manual. Oh, it's still got a lot of this going on though. That's nice. Pin detector. Ooh, and they talk about the connectors in here in case I need to redo the wiring harness for some reason. This looks like the same internal connector that we were seeing. That's nice. Neat. That looks pretty much the same. I wonder what the differences are between versions. Oh yeah, so power, so this thing wants 5 volts. I have a choice to make about where to get the 5 volts for this. The input to this whole gimbal system is 12 volts. There are a bunch of places where that's converted to 5 volts. Like basically every joint in the gimbal and the camera all have their own separate 5 volt buck converters. So the way the gimbal was originally designed, it actually provided 5 volts for a GoPro off of the last of those buck converters in the joints. So I could use that. I already trimmed one of those wires pretty short, but I could deal with that. I could solder a joint there. It's also tempting to pull it off of the camera, since it might have maybe a buck converter with more spare capacity, and it might be more mechanically convenient to access. So I might take a look at the buck converter that the camera is using and see how much spare capacity it has and see whether that would work out. And then just give it 5 volts off of the camera's buck converter. Oh, interesting. So Sodium points out in chat that the PCB image they use in both datasheets is identical, aside from some color balance modifications. It also looks like these are the same housing drawings, which these will come in handy really soon, I think. This back panel being separate might be useful. In fact, I might just not put the back panel back on. Do these screws still fit without the back panel mounted? Because I don't know that I want those ears. I mean, I might basically yeah, these need something there to prevent them from going too deep in the shaft. But it's tempting to replace that back panel with my own 3D printed bracket, basically, and just use that to hold the whole thing in. Since I think the mounting ears that are usually on there might be too sticky-outy and might get in the way of the camera. Don in chat is betting that the only difference is in the firmware. Yeah, that seems likely. Well, the firmware or the FPGA bitstream. Okay, so will this run in a continuous mode, or do I have to give it a trigger? Let's find an actual dock for the PWM mode. So, okay, so it looks like as long as this is pulled low, then it'll kind of pull back high in response like this. So that's great. I think that's what I want. Let's get a little tiny breadboard and a 1K resistor just to have this match the datasheet. Tiny breadboard town. I wonder if they have a electronic version of those CAD drawings, because that would be more useful than having to type those in myself. I'll probably Google for it and see if somebody's already modeled it. Seems like they would have. Oh, a cat is seriously catting it up over there. Oh, yeah, Don clarifies. When I said firmware, I meant the FPGA image. Yeah, okay, that makes sense. Yeah, the boundary between software and hardware is so fuzzy as to be almost non-existent these days. Here's a 1K. Like, I mean, lately, like, I spent some time recently working on this SD card emulator for trying to determine file names that are interesting to a particular bootloader that I'm stuck in another project. And really the main difference between firmware and software at that point is how long it takes to recompile. All right, so red, stick somewhere just to keep it out of the way for power. Black over here will be ground, which is also going to my 1K resistor because it's pulling down to ground. Then that looks like third from the red pin. And then these other 3 wires I don't need. And just to keep them from shorting right now, I'm going to trim the stripped portions off, but I'm not going to trim them extra short yet. I might trim these shorter later. So when this goes to that side of the 1K, let's put some grabby bits in here so that I can put some grabbies. Just some random little bits of header in there that I can attach probes to. All right, so oscilloscope. Let's go back to default land. So this will just be across the 1K resistor, basically. Ground and the multi-purpose bidirectional mode pin that we've got. And now I just gotta run 5 volts into this thing. Let's take the power supply off of the motor and set it to the right voltage. Not blow up our LIDAR module with 24 volts, that would be sad. What is my current limit set to? Ooh, 3 amps. That's like motor territory. Let's bring this down to more like a half an amp max. And 5 volts. I don't currently have a good camera setup to view my power supply, but it's probably just as well because it's not a very photogenic power supply. It's still got a broken segment on the current meter. I opened it up once to repair it, and it worked for a while, and then it stopped working again. So I think I just need to hit, it's got like a bunch of headers that connect the segments on the segment displays to the board, and I think I just need to blast those with contact cleaner some more. Oh, that's neat. Dr. Toon points out that the Robot Shop website, Google for Robot Shop LIDAR Lite, has some good comments, has a good comments page on this sensor with lots and lots of FAQs answered. That sounds nice. Sodim says, I continue to be amused by we'll just recompile the CPU. Yeah, it's been fun. I like working on that kind of stuff. And it's been so nice to just, like, oh, I need another hardware module. I need like a 64-bit counter that I can just latch when this event happens. I'll just write one in 10 lines of Python and recompile the CPU with that module. So that's been super fun. Okay, 110 milliamps, and we've got some pulses. Let's get the scope triggering on this. Oh, there's a visible LED on the back here blinking. Let's see if I can get that on the camera. That little red bugger, I didn't even notice that among the sea of surface mount components, but there's a little visible red LED that seems to blink when this thing is operating. So, okay, how is this actually supposed to be represented? Oh, there's a lag on that video of the scope. So it looks like it's just pulse width happening. Oh, I don't know if it's just me, but it almost feels like there's some warmth coming from the transmitter, but I might just be imagining that. Anyway, let's point this up. Maybe somewhere. Oh, yeah, that's the ceiling. Okay, let's not worry so much about the retransmission rate, because that's going to bounce around a bunch, and let's just look at the actual pulse length here. So that's all the way up at the ceiling, which is pretty far away. Let's see how, let's get a better camera angle here. Clampy clamp clamp. So, oh, that's nice. I'm going to try to move a little slowly so you can see the response, because there's a little bit of a lag on that video relative to the camera. But I'm looking at it in person, and it's very nice and smooth. Let me see if I can get the camera pointed at the actual O-scope. This button. Okay, so you can see the O-scope. It's not very big, but so here I am entering the beam. I also want to get an idea of just how wide the beam is. Well, I also want to know just like if I have the camera. Let me try to get this on the frame. Is this too much to ask to get everything in frame? This is seeming like it's going to go really nicely on the gimbal, assuming it mechanically fits. This is already getting a little bit warm, but it's only drawing 110 milliamps, so I might just be imagining things. Actually, I have a device for this. Thanks to Kyle. Oh, it's over here charging. Let's stop touching this for a sec to avoid the body heat, making it warm, and then just actually use the thermal camera. What is that? Oh, that was hitting my microphone. Yeah, that's a nice narrow beam. This is going to be good. So there's that. Let's zoom into just that level. Yeah, I like this sensor already. Kind of makes me want to use 2 of these on the robot now. But then I think I'd have to trigger them separately. All right, let's get this on the screen. Ooh, phone, come on, case. Pardon the camera change. key for this other layout yet that gives me more room for the camera. Oh, and is it way over there? There we go. Okay. A few interesting things I've noticed even so far. That, man, so some of that wiring is a little warmer than I expected. I went and checked it to make sure it isn't overly warm, but just, I think the floor is actually pretty cold. But this big snaky one right there is the cable that's carrying like 500 watts of power to run all the equipment on that side of the room. So, you know, of the things that are warm down there, it certainly ranks. That box over there that's now looking pretty bright is the, I think it's a DVI, or no, it's an HDMI splitter for the microscope, or something like that. Anyway, we wanted to take a look at this. Oh yeah, so there's a little bit of warmth to it, but let's see what it looks like on the back side. That is the power supply for the emitter, and the FPGA being the warm spots, as you would expect. Can we get a measurement? Whoops, it is attached. Grr. Oh, weird. I guess the phone sounds are coming out through the big speakers since I've got it remoted. That's nice. Okay. 80 degrees or so. That is fun. How about the cat? How's Cat doing over there? What is that? The bottom half of the image is totally calibrated differently than the top. Can I... Okay, that's better. I might have released the shutter while it was calibrating or something. Okay, that seems better. Good cat. Let's see how much power we have available for this thing. So it's still hovering around 120 milliamps at 5 volts. Let's see if we can find the 5 volts power supply in the camera and see how much capacity it seems to have available. This is going to be great for keeping the camera focused. I'm really happy with this so far. And, you know, I think the other thing I wanted to check was if it's mounted, you know, near the camera, is that going to obscure the view that it gets? So if, you know, I'm not going to mount it on this side probably, but I guess I could. But, oh, that would look super bizarre with like 3 eyes right next to each other, moving around like this. But if I mounted it further back like here, I was wondering whether I would have to worry about this lens obscuring the view, and it looks like not. Like it looks like the laser is so narrow that I can pretty much go as far back as I want without having to worry about that. So like up here, you know, for example, I have to be right about there for it to actually start sensing. That's really nice. That's going to be easy to design for. So for data, I just need that one pin, which I think I can handle getting through with the 30 gauge silicone wire. For power, 5 volts. And then just updating our bracket design so that it actually holds this. And that might be... I like the idea of just designing our own replacement back panel as part of the bracket. I think that might be the best way to hold this without the mounting ears taking up a bunch of extra space, but we can resolve that problem with the help of CAD. Yeah, a little warm to the touch, but not even really barely noticeable. Okay, put this aside. Camera tone. Let's see if I can see what's going on without taking this out. Well, I guess I should get this right, easy to take out, since I'm going to have to move things around to play around with the center of gravity. So, might as well unmount this. This is still in the same state that I'd left it on a previous stream, where the coax that I added for video is plugged in here, and that seems to be working really nicely. These two bolts are holding it on. I've got these temporary spacers because I used them to adjust the center of gravity without printing a new bracket. And they seem to be all right so far, but I still think I'm going to replace the bracket with a new model that holds the LIDAR. So I've got these two bolts, the coax, and the power still is not actually connected because I hadn't decided on what kind of connector to use for that. And so now it's looking like maybe I want to find a connector solution, which could be something that plugs in where the wiring harness originally went on this camera, or it could be something separate that I hack on. Some kind of connector system to get 12 volts in, and it looks like now I want it also to get 5 volts out, which seems like that might be easy to pull off. If for whatever reason I can't get 5 volts off of this board, or don't want to put the regulator through that, then I could just pull it back from. So there's also 5 volts available at this joint, which is pretty easy to get to, and so I could just run a wire to that while I'm running the wire for the PWM output. So that's not a big deal, but if I can get it from the camera, that would be a little more convenient, and would put a little bit less stuff into the gimbal. So I think it's at least worth checking. And my plan there is to just look at the camera's input power consumption and look at the design of the buck converter and just see how much headroom it seems to have. I mean, it kind of surprised me a little bit that they were running a GoPro off of that little buck converter in every joint. Because, you know, like charging a GoPro over USB can, you know, it's probably going to want like half an amp at least. And each of those buck converter will also be running, you know, all the local circuitry, which admittedly isn't much. So it's probably got a decent amount of extra capacity in most of the joints. I need a smaller screwdriver for taking this wiring off, I think. I also don't really want to move this right now. I'll undo this screw that's holding the wire. Oh, that's not Phillips head. That is... That's why I don't have the right tool for that. Do I have the right super tiny hex key within reach? I don't think I do. Let me grab that. I got a blue background now that that's under the microscope. So, oh, was it either of these? I feel like it's probably not either of these. 'Cause it's bigger than this, right? Probably means it's on the desk somewhere. This is like a 1.5 millimeter hex key or something like that. I might just go to my bin and see if I have another one handy. It might be faster than trying to find the specific one if it's not actually where it's supposed to be. Unless it's in the other bin of stuff for this project. Maybe I have another one in this bin. Oh, is this one? I think this is the right one. Yay, the joy of having the right hex wrench. Oh, wow. Yeah, there's some talk about the scopes in the chat. Yeah, the scope I have right now is super fancy. It was a really amazingly lavish gift. I appreciate it quite a lot. So, yeah, the scope I'd been using previously was a lot less fancy. It was like kind of a mid-range Rigol that I paid, a few $100 for. Whereas this scope is like fancier than any car I've owned, and I don't currently have a car. It's a pretty nice object. And Doomel29 in chat is saying the front-end ASICs on the scope have a coax connection going right to the die. Yeah, that sounds about right. It is a very nicely made scope in all sorts of ways. Like it's got enough bandwidth for some of the crazier experiments I've been doing. It's also just got some really nice functionality in terms of UI and decoding and all that that's nicer than any other scope I've used. But as I was saying earlier, it's nice to see some of that make it into the lower end Keysight scopes too. That's been nice to see. Okay, hopefully that didn't just break anything the way I ripped that coax off the camera. I think it's fine. So we can see what we've already plumbed into the gimbal, coax and 12-volt power. So let's see if we can get some more mileage out of that 12-volt power before we think about running additional power wires back there. I'm also tempted to take this off the gimbal, but I think we want to leave that on so we can do center of gravity tests. So here's the camera. Let's find its power supply. Oh, there's the chip we're interested in on the other side of the board. I see the inductor and the diode on this side. I think the controller might be back on the other side. Let's take this board off again. It's only kind of tacked down with 2 of these standoffs anyway. I don't actually have the right size bolts to put this in for good, but I think I'm going to cut some slightly longer bolts. I just haven't gotten around to doing that. These standoffs are super annoying. Alright, so there's the board with its beautiful sensor. And yeah, I think those are the power supply parts on this side. So let's take a closer look at those under the microscope. Let's just first of all maybe find out where the 12 volts goes just to get our bearings. Let's get the wiring harness for this and start there. Also maybe put on some anti-static. I feel nervous working around something like this without the anti-static. Here's the wiring harness. I can imagine this maybe even having access to 5 volts because it's got this little joystick button. And, maybe they did that as all like pull downs to ground, but there might also be some reason that this part had 5 volts. So I'm curious what this pin out is actually like. Oh geez, the Apple TV did the thing where the phone lost connection again and it went back to the screen full of advertisements. Change that before I accidentally switch to it again. Alright. So, let's also maybe put this in a vise. Yeah, will this fit in my vise? Carefully. Oh, that's great. Will not damage the sensor this way. Okay, so there's the connector. I would like to keep that connector somewhat free so that I can just still plug this wire in there whenever I feel like it. So I think even if there is 5 volts on here, I can imagine just putting on my own connector, just like PCB surgery, a connector that gives me 5 volts ground and 12 volts for this particular purpose. All right, so let's put this in just to do some continuity testing. It seems to be in. Let's get the meter on this DC jack. And first, let's just see where ground is going on this connector. Poke myself to test it. This task clearly deserves another sticky note. Let's keep these in order. Maybe I need a little book full of sticky notes. That's how to solve this problem. I mean, eventually they expire, like they just aren't useful anymore, and I cross out parts of it until the whole thing is not useful, and then I throw that away, or I put it somewhere else. I don't tend to keep sticky notes relevant for that long. It's more of a short-term filing strategy. One of these pencils. How many pins are we dealing with? 10? Bottom one is no connect, so really 9. I drew that a little long, but 10 pins. Can I get the camera on the screen? I'm going to assume this one is 1 because they would probably not start at the end of the connector, and that's 10, but we'll look for some confirmation. Is there any kind of pin 1 marking? Yeah, that looks like pin 1, unless that's just the marking for the diode. I'm going to already guess that that first pin is 12 volts because it's going right into a reverse protection diode, and it's red, but we'll do a continuity test. So first of all, I want to see where the ground goes. Black pin does seem to be it. That's also ground. Maybe I want colors on here too. Oh, this is way too small. I'll label 10 as a no connect and then just have 1 through 9. And then wire colors, that'll be red, yeah, black, yellow, blue. I'm going to guess the yellow and blue are the composite video. We have brown, white, and what is that mess going on? Is that another yellow wire? It looks like orange. Yeah, that's orange. Orange, gray, and the colors are not very good on this microscope. That's actually green. The colors are easier to see, and oh, maybe it's on the monitor I have connected to the microscope. They look better on that monitor. I didn't go out and buy like the best monitors for everything in the shop. I've got like a nice monitor on the machine that I usually use for editing, but most of the monitors around here are just like the cheapest thing I found that was easy to mount. Green, gray, orange. Okay. So then grounds we found were black and blue. What else? looks like green. So I'm guessing that this is going to be 3 blocks of signals, one for power, one for composite video, and one for the button pad. This isn't enough for the joystick to each get their own separate buttons, but they might be multiplexing them somehow, or using different voltage levels for different directions, or otherwise saving wires. So anyway, I'm not going to go into huge detail, but let's at least verify a couple of these assumptions. Composite video is indeed yellow, and 12 volts is indeed red. So I doubt they would have a reason for 5 volts on any of these. It looks like we have 4 pins that are all being used as button I/O, and then they all have resistors in series here. But, you know, since we have a total of 5 buttons, that would require a little bit of multiplexing at least. Anyway, we can ignore most of this. Let's trace out where the 12 volts goes. So, reverse protection diode, we have, and that looks like, it's going through that like a pass diode. It's not like a clamping style, so it goes open circuit when you plug it in the wrong way, which is good, but the trade-off is now that diode's always burning a little bit of power. So then it goes into this capacitor. So this ceramic cap should have our full input 12 volts across it. So this node over here should be ground. So this I would expect to go into one of the buck converters, those 2 vias. Let's see if we can see where those vias are going. I'm going to unplug this wire just to make things easier. Hard to see exactly, but it looks like it's going into that chip, the IF8GA. So I'm guessing that's the transistor for their input buck controller, and that's the actual controller chip. Looks like that's the transistor gate, and then these are like series resistors on the MOSFET gate. That's going to be my assumption at first, but let's look up these numbers just to see what's going on and see if we can get some current ratings out of these parts. So I think both of these might be relevant, but probably more so the MOSFET. Mouse. No, this one, yeah. Does that say? Oh, that writing is so annoying. That is UTC BA6208G. Let's look at both of these parts. UTC, the Unisonic BA6208. Oh, motor driver. Interesting. Either this is wrong or they're using a motor driver as a power supply controller. Is there any reason for them to actually have a motor driver chip on here? Oh, maybe that's actually the motor driver. So maybe this is the optional. So I think that's actually connected to this thing, which goes off to the, like an optional focus motor. Okay, well maybe then this is either an integrated controller or this whole thing is separate from the 5 volt supply and we need to keep looking. So let's see what that IF8G is, 8GA. IF8GA, maybe this isn't a transistor. Huh. any of this right? LM2736. If this is right, that's a nice amount of current, but I don't know why this showed up in the Google search for that marking. Let's see if we can find the package marking here. Or maybe just search this for IF8G, no? Why did this show up? Is this like a related part? This is only in, oh no, that's the right package. That's a 6-lead SOT. Markings? Do we have markings to identify the package? This certainly could be it. Oh. No, that's a different marking. Shab. Shabababa. Okay, let's come back here. That doesn't have anything useful. No, well, that's interesting. I wonder why this Texas Instrument part came up. Search for, is there any chance that's a different interpretation? Oh, there's a couple of these IF8GAs. 3 of them, actually. There's one here, and one there. Each one next to its own coil, so definitely looks like some buck converters. Why would they have 3 separate ones? Unless they're, I mean, maybe they're all different voltages, but... Okay, well, maybe I'll just power this up and poke around to see what voltages are present on those. I would like to find a datasheet for this part, though, to at least see what the current rating is, to see if I'm even barking up a reasonable tree. Don Beckham in chat is saying that this LM2736 is probably the TI version of this part. I assume that's why Google is telling me this. It's just, this is one of those like AI results where, yeah, there's probably a correlation somewhere, but I don't see it. And it'd be nice to know why I can trust this result, if I can indeed trust it. Because if that is the right part, it means it can handle 3/4 of an amp, which means it should be fine to throw my LIDAR on there. Well, maybe that's a close enough bit of evidence for us at the moment. Let's at least see where we can get, like if this is intended to be the same part, let's at least see if the pinout matches. So we've got boost, ground, feedback, enable. Let's at least look at the reference schematic here. There's the internals, which seems about right. Boost. I assume they're using this in buck mode. Anyway, it looks like you can connect this in various ways to get different power supplies. Anyway, let's just probe around here with the oscilloscope and see what's going on. So that was boost, ground, feedback, enable VN switching node. Okay. I guess we want the scope on this. How is there not an O-scope plus microscope channel, or did I just put that elsewhere? have an O-scope plus microscope channel. I think we can get by with this camera though. That's probably something I should throw in my setup. Are we not so servo? I think we're not very servo at all right now. What's going on? I think the camera is just way too close. Oh, that'll do for the moment. I just want to poke around here and get some voltages. I don't necessarily want the most vivid cinematographic experience at the moment. Even though that's always a nice thing when you can get it. Power. I think I do want this just plugged in and operating normally here. Oh, I don't know if the sensor is going to be happy with running with this much light around, but it's probably all right. I mean, this thing has to deal with, like, daylight. It's just, you know, not going to be in focus or anything. I think I actually wanted that to be mounted the other way, just for easy probing around. Okay, so yeah, just on this part of the board, I see 3 of these IF8GA chips that all seem to be separate buck converters, or some converter. And then over here... Oh, interesting. That's another interesting chip. Let's go back to the microscope briefly. So yeah, 3 of... So left one, that's the motor driver. Then we've got 1, 2, 3 power converters. Then that's the SMA output, presumably going right to one of those ASICs on the backside. Then what is this one? This says Berg Micro. That looks like it's a spy flash with the firmware on it. And then either a flex for some lens-related thing or a debug connector. More passives for the big old chips on the other side. Well, so all the power conversions up here, I only see 3 of those. And I don't see, where's the inductor for this one? Is that on the other side? So these 2 have an inductor kind of cozy nearby. But what do we have for this left converter? Oh, its inductor's on the backside. It also has a big old tantalum there. I think that's the one that we're going to see for the first stage, but then maybe what we're going to see is, you know, the first one bumps that down from 12 volts to 5 volts, or maybe some other intermediate voltage, and then we see like another one of these giving lower voltages for the other chips, or possibly higher voltages, since these could be boosts, but let's see what's going on. I think we have this ready to plug in. Plug. So let's run this at 12 volts input. That was drawing more current than I expected. That was like 400 milliamps. Is there something wrong? Is that related to the light that it's being exposed to? Like, let me try turning the board over and then powering it on just to see if there's a difference. I might just be overreacting. I just thought it was lower power than this. 400 milliamps. Fluctuates a little bit. Did not think the board was quite this power hungry at the 12-volt rail. I just want to convince myself that this camera is not breaking itself, so I might try plugging in the video output just to see if it's operating. Maybe get a shorter SDI cable than the monster I was using before. I mean, it's always nice to have this camera ready for a test, right? Oh, cool. Don in chat tracked down the IF8GA. So we still don't know why the Google results were just finding this thing, but apparently it's a Chinese clone of the LM2736. So probably reasonable to expect it to have about a 3/4 amp capacity if that's what it's showing. If this camera is supposed to draw 1/2 amp at 5 volts, then we still, I think, have enough room, but it's tighter than I expected. I'd remembered this camera being a little less power hungry, but I might be remembering wrong. So, okay, this should be streaming from the SDI input. Let's make that a little bigger. And then we'll go. Currently, the only cabling I have that actually will work for this is the one in the gimbal, so we're going to go use that. Alright, so that's going to the Blackmagic capture board. On the gimbal. And then how long is this wire? Kind of long enough. It will not really fit into the microscope, but I can bring this over here. And then this plugs down onto there. Okay. So, let's see if this operates. 12 volts, 400 milliamps. I don't see any video. Just check over all of this again. I also try the composite output just in case that's a thing. Might also try putting this in the housing just in case that matters. Might also try testing this SDI input to make sure that's actually working. Well, it's sitting there in the housing. Just briefly put it in with one of these little screws so it doesn't fly out immediately. Okay. A little bit less current, 390 milliamps. It's fine. I mean, it's fluctuating a little bit like it's booting or something. Let's find a way to test this SDI. Maybe borrow the cable from the cat camera. Oh. So many layers of debugging. that the one I wanted to unplug? I don't think it was. Well, maybe my SDI capture is not working. That's a good sign. That's better than the camera being broken, I think. Do I have to restart this? Need to unplug and replug the capture box. Always have a control experiment. Oh, Wildmania is asking in chat if this camera is a 720p IP camera. It is not. It's in about the same container that I've seen a lot of IP cameras, but this one's actually SDI and it's 1080p. But you can get a lot of similar cameras in approximately the same shape online. Let's see if that's what I wanted. Yay, okay. Control experiment is now controlling. Let's see if I can get my other camera to come to life. It might just be this camera uses a lot more power than I thought it did. Now I'm trying to remember like under what circumstances I last measured it, because maybe I haven't measured it on its own for a while. Okay, that's plugged in. Power. Oh, the current consumption is a little lower. Maybe it likes having a properly terminated SDI cable. Still don't see a video, but is that just from it sitting on the table? Did the joystick do anything? Oh, the joystick lowers the current consumption briefly. Is there something wrong with this cable? Oh, geez, maybe I plugged the cable in upside down. Shit. How is that possible? How is that possible? I don't think it is. I think I did not. I think this is right. I think I'm just looking at this at a different angle than I'm used to. Because, yeah, this cable is... Okay, the plug is definitely keyed. This can't fit upside down. So, what is going on? Does it behave differently on a slightly lower voltage, like 9 volts or so? Oh man, it's drawing a lot less current off of 9 volts. 120 milliamps. Oh, this is annoying. Did I break something? Oh man. Well, this is annoying. Can we see what's heating up as I power it using the trusty thermal vision? Is that, I mean, I don't want to like break anything, but if it's heating up a little bit, maybe we can tell. Touch your camera. I'm also getting a little tired and it is kind of late. I might think about what to do and Wildmania is asking what the connector is on the piece of coax and whether that's interfering with the camera. I'm forgetting what this is called again because I didn't know until someone else told me on a stream. I think I want to say MCX, but that's the SDI video output, and I don't think it's interfering. Like, it doesn't seem to be shorting anything out, and you know, I mean, we can check to see if we're getting any data out over that, which might be useful, just like with the scope, although I'm guessing that something is going wrong at a slightly more fundamental level. This is all frustrating. I just wanted to put LIDAR on my cat camera. Oh, I should have held that more. There we go. At such a close range, I kind of need to not rely on their image enhancement because the cameras don't line up well enough. But what you're seeing now is mostly just the shiny areas reflecting light. So I know that the camera normally should give me an image at like 9 volts. So I'm going to try running it at 9 volts where it's not actually consuming much power. And then maybe see if I can see anything getting warm and or see it actually produce some video. A lot of shininess going on here. It gets cranky about the calibration if I'm covering up the sensor partially. Seems like maybe something on the other side is warming up. So, I mean, since the case doesn't seem to be relevant, I'm going to take the case out so I can get more of the board in view. We're getting some FLIR background in the microscope. FLIR. Let me try to clamp this into the vise with the power side facing up so we can take a look at it. Oh, maybe we have a repair on the power side rather than just trying to see if it has extra capacity. That would be embarrassing. I don't know how I could have broken this already. Oh, we wanted the other side, didn't we? I didn't actually flip this around, I just viced it. Let's try to keep the coax. You can give this a little more closeness. Alright, so there's the coax going off to the gimbal. There's some wires that we don't want it to short against, even though that's not powered. And then there's the camera board. And here's our thermal view of the power board. A little bit out of alignment. I don't want that image to be distracting me when I'm looking for something in particular, so I think I can safely put a piece of tape over that lens without actually having it stick to the lens. And then I'll be getting just the thermal image, which is what I want right now. There might be a way to do that in software, but this is easier. Now the camera's having a hard time focusing on it. So nothing warm yet. I'm going to plug it in. So 9 volts, 120 milliamps, no video. Looks like a little bit of heat on the bottom right side of the board. Might just be my imagination. There aren't any components on the board on that side, but it might also just be the environment or some reflections. Oh, it might also be helpful to compare this to a working camera to see what the differences are. This is just an unexpected bit of unexpected debugging. I wasn't expecting to have to debug a broken camera, but I guess that's what we're doing. How alive is this as far as the oscilloscope is concerned? I wonder What if I'm just going to find like a conductive debris problem here? Where can I grab ground? Guess I can grab it from over here, even though that's not actually great. Alright, so it's still plugged in. That's 2 volts per division, DC coupled. So we decided the first power supply was this one up here on the left. A lot of zeros so far. Am I remembering the pin out here wrong? Let's unplug that and go back. There might be just a really dumb short somewhere. Wildmania is asking about the SDI output and whether it goes to the right input. I'm not quite sure I understand your question. I did test the SDI input just now with a different camera to see if it was operating. I mean, and I've used that coax before successfully, so like that shouldn't be just like not at all working. It should be at least partially working. Catductive debris. Yeah. Anyway. Oh, it's getting late. I'm starting to lose my train of thought from it just being tired. I still don't understand what Wildmania is asking. You're saying that I separated this coax. I really don't understand what you're talking about. Sorry. The SDI video signal goes from this little connector on the board through this little coax here, up through the gimbal, then into this connector, which is a little off frame, and then into the box that I'm displaying it on the computer with. So I think that whole path should be working. Anyway, I was going to look at the pinout for this again to see if we're getting power in the right place. Boost voltage, ground, feedback, control, input supply. Okay, so we can find pin 5. We should see the input for each of these converters. So let's plug this in again. 9 volts, 120 milliamps. Scope. And we find our 12 volt input anywhere around here. That should be the input voltage, but it isn't. Anything over here? Can we do a control test to make sure this is working? I really want to poke this into the input 12 volts, but it's only really accessible on this side. Why am I not seeing that? Why am I not seeing that indeed? Is this a problem with my wiring harness? Ooh, maybe this is a really stupid problem. Let's unplug this. Did I crush one of these wires when I was mangling this connector earlier? It looks fine. With that unplugged, okay, the cable itself is drawing 120 milliamps. How is that possible? Do I have something else plugged into this power supply? Oh, shit. This was... I had these cables wrong, and I was just putting 12 volts into the LIDAR light module. I really hope I didn't do that long enough to damage it. That explains several of the things that just went wrong. Let's see if the LIDAR module is still working. Maybe it is too late for hacking right now. Alright, let's try the LIDAR module. 5 volts. Now it's back to 110 milliamps. I see the light blinking. Okay, maybe I didn't kill it. Series of embarrassing failures. Where's my little hooky bit? This thing? I think it's still working. Yay. Okay, well, I just tested that it will survive brief overvoltages with some current limiting at least. That's unnerving. I hope I didn't degrade its performance too much, but I think it's fine. If I need another reference unit to compare it against, I do have a couple more of these sensors, but I think it's fine. Oh, and it looks a little laggy on that screen because of the video, but if I look at the real scope, then it actually seems to be right on target, so I think it's fine. Okay. Back up a level in the stack. Let's unplug that. Let's remove that cable from this situation so I don't do that accidentally again. 110 milliamps at 5 volts. That's happy. Now let's go back to this board. Get it powered up properly, with an emphasis on the properly and on the powered up, and on the not powering up things that shouldn't be powered. Maybe being optimistic, but I'm going to go back to this SDI monitor and see what we have. Whew, that was a close one. I think we avoided disaster there. Let's plug... Oh, the coax is plugged in. That's plugged in. I think I just need to give this power. Okay, into the right circuit. The right voltage. Okay, now it's drawing 120 milliamps, which seems more normal. I'm not getting any output, but that might just be OBS's fault. Oh, or there it goes. Great. Oh, that's interesting. We're getting some interesting patterns. I wonder where that pattern is coming from. Is that like some interference between the Bayer mask and the scaling here? I think so. That's funny. What kind of scaling is this doing? No filtering. Well, there we go, maybe. Maybe that didn't help. Oh, it's probably this scaling. Maybe not. Is there a separate preview scaling? Anyway, that doesn't matter so much. We know the camera seems to be working. We can get maybe a better idea by putting it in the housing with the lens. Might do that just briefly for my own sanity, if one may call it that. And that is this arrangement. Just gonna hold this in position. Okay, so now the camera is using 120 milliamps at 12 volts. And takes a sec to boot up, I guess. There we go. Yay, that's looking much more better, looking much HRD. Only the Hest of Ds for our cat robot. Speaking of cat, there's a cat over there. Oh yeah, if I slide the board around in the housing the image moves around, and you can also see vignetting on the edges if I move it kind of an extreme way. But it's remarkably tolerant to the board shifting around a bit. Like, what if I move it back a little? Yeah, I can shift the focus plane for sure. That seems to be pretty focusy. Great. Let's probe around on these power converters now and see which one goes to which voltage. The problem was no lens. Yeah, definitely. That was the issue all along. Okay, and the converters are at the top there. I really like to have a setting for microscope plus scope. Where did that one go? Oh. I can turn the microscope on this screen. That's how I usually do this. Or not the microscope, the O-scope. I guess I don't have this on here already, but I can add it. Video, no. Man, using OBS with a terrible mouse is an experience that I really should stop having. Okay. Okay, little O-scope in the corner. Let's see how that serves us for the moment. I'm going to unplug the SDI cable because it's kind of still precariously connected to the gimbal, and I don't think I need it at the moment. Times like this, I'm glad I have a connector. Don in chat is enthusiastic. The problem was no lens. Bingo! Yay, me again, lol. Basically. Oh man, I've got a really chowdery edge on this microscope now from hitting it with the soldering iron a bunch of times. I still like the way that looks. Oh, Tuco, are you ready to play Bolt? Okay, I think that's the one that's going to be our main 12-volt input, but let's take a look. Man, noticing that there just was no input into this thing that was overcurrenting was a pretty good clue. I just feel sad that I was just torturing my poor LIDAR device over here on the side. I mean, it probably wasn't passing 5 volts directly into the FPGA. I was probably just stressing out some poor little LDO on there. Oh, that's an interesting question. Don in chat also asks, have I done a video on my camera/streaming setup? Not like a proper edited video. I've done a couple, like 1 or 2 streams now where I started it out with a bit of an intro to the setup. So I think if you search my YouTube for something about streaming setup or behind the scenes, I think there's a bit of that, but I didn't do like a really organized video on that yet, so that might be still a thing to do later. Alright, let's get this grounded. Tuco wants to play. Oh yeah, and as Ben reminds me, I do have some notes on GitHub. If you search for scanlime on GitHub, I've got a repository called Broadcasting that has a bunch of notes and scripts and stuff that I use to get this stuff done. And that's maybe the most organized collection of information on this I have so far. Okay. It seems to use a little bit more current when the SDI is not plugged in, if that's my imagination. Or if that's not my imagination. I don't know if that matters, or if it's real. That is our 12 volts. It's way off the scale. Cool. That's our 12 volt input. That is a switching node, I think. Oh no, that's the boost capacitor. This is the switching node. So the boost capacitor is the switching node plus some extra voltage to drive the N-channel FET. Then this is the output before it gets any filtering whatsoever. And then the filtering is going to be happening, it looks like, on the other side of the board. So let's flip this over and take a look at the voltage on the output of that converter. So that was over here. If this is a 750 milliamp converter, then I think we've got plenty of spare capacity, and I should be happy to run the LIDAR off of the same power supply. So I think we want to be looking at this little complex with the, I don't see a diode. Maybe the diode is on board? Is the diode built into this converter, or is that separate? Diodes are external. Which kind of makes sense because that you configure the diodes differently for different switching topologies. Anyway, let's go back to this. Oh, that explains it. Sorry, I was getting confused because I'm like, where's the diode? And I'm like, well, it's there. But so this is the diode. I was ignoring that at first because I thought that was the input protection diode, but that's this one over here. So I think this is our switching diode, and then that's the capacitor, and that's the main switching inductor. I think this might be a filter choke. Let's probe around here with the scope. With it on. It's on again. Oh, this has also got an LED. That's normally hidden by the case, but that'll be shining while this thing operates. A little bit of light from the CAT-CAM gimbal. So, is that the positive side? Or is that negative? Oh no, that's positive. Ooh, this is pretty low. I wonder if all the buck converters are going straight down from 12 volts to whatever their target is. That is like 2 volts. What is this one? Same. Also 2 volts. I would expect to see the switching pattern, or the switching noise across this a little bit, but under such a low load, I guess there's not going to be much current going through this inductor. Yeah, interesting. 2 volts. So maybe this is like a core voltage for their ASIC. These are the tantalum filtering capacitors for the other 2 power supplies. So this might be the easiest place to get the other voltages. Let's see what's over here. That's 3.3 volts. And, ooh, that's even lower. That's like 1 point something. Does this not have a 5 volt rail? That's the switching node for the 1 point something converter. Yeah, that looks like 1.2 volt rail maybe. Okay, so yeah, 1.2 volts and 3.3. I would have expected this one to be 5, but I think that's 1.8 volts. Okay, no 5 volt supply in this. I guess we're getting it from the gimbal or adding our own. That's 1.8 volts. Man, no 5 volt supply. That's a little weird, but all right. Good on ya for not needing one. Oh yeah, Wildmania is asking what the bandwidth of 1080p on SDI is. There are a few different modes. I think I'm using it in the 30 frame per second 1080p mode, which I think is 1.25 gigabits. All of this is 3.3 volt logic. Well, I think I can pull the 5 volts through the gimbal just fine. I mean, it's designed to power a GoPro. It should be fine powering a LIDAR sensor. The LIDAR sensor is a lot lower power than the GoPro. Okay, so that's our plan. It's not optimal, but at least now we have a plan. So basically get the power from the DC-DC converter that's on this circuit board, which normally powers the microcontroller on here, and the IMU on here, and optionally the GoPro you're attaching here. So I'll basically be pulling it off of this circuit board that already has this wiring harness dangling off of it. And then I think the next step is to look at the center of mass. So I actually want to do some CAD. I think it's probably too late to get into that. I think I'm going to run out of steam before I make any real progress. But let's at least figure out roughly where to place things so that I can be thinking about the design. Oh yeah, so this also informs the connector on this camera. So there's no useful 5 volts on here, just 12 volts in, which means I think what I want to do is somewhere on this board where it's convenient, either attach a couple, well, maybe that's the easiest thing to do, honestly. I've got some like JST male and female wiring connectors. It might be easiest just to take one of those JST connectors, solder one end down here to the biggest pads available, so probably grab ground from somewhere, attach power to that diode, and then, you know, glue that down for strain relief, and then I can just plug that into the gimbal side of it when I attach this. I could use this connector. I'm just trying to keep this open so that I can plug in my little joystick when I want to. Oh yeah, and Wildmania is also asking, because they want to know what the length can be like for these cameras. Actually, one thing that's relevant, so I mentioned earlier that I've been trying to get this signal through this like reclocking signal repeater thing as kind of a way to clean up the signal if I have to run it over a really bad coax. I think that might not even be necessary, but let's take a look at this product really quickly, because I think this is actually kind of interesting. Was it this one? It was either this one or something similar to it. So kind of on the expensive side, like about as expensive as the camera, honestly, but seems to actually do a really good job of repeating the signal. And somebody who's selling these had some specs on it, and I think they were recommending using one of these every 350 meters. Oh no, here it is. So they're saying 350 or 300 feet for 3G SDI, 400 feet for HD SDI, just using one of these repeaters and then extending them. And they're saying that there's no limit to the length because you shouldn't theoretically get any bit errors. It just ends up, you know, adding more delay. This is an interesting device too. I forget whether I've taken one of these apart on the stream already or not. I think I might have taken it apart for my own information but not shared it yet. It basically has the kind of chipset you would use to get SDI into and then out of an FPGA, and then those are just glued to each other. So it's kind of nice. Let's see, where to? I wanted to mount this board back in here just to have the weight approximately right, and then we can just kind of hold this in position to see where it should go. I think I still don't have screws that are short enough, but once we get a little further along, I'm going to just take some M2 screws that are almost right length and cut them to size. I'm just going to put a couple of these in just to get it lined up for weight distribution purposes. Oh. I'll just put 2 in the opposite corners. Oops. Oh, you know, I think that this originally only had 2, because yeah, the original back panel actually just used these 2 corners to hold it down. I don't know if that was an intentional mechanical design to avoid warping the board, or if that was just to save money. I suspect it was the latter, but I'd be willing to listen to arguments either way. So there's the camera with its full girth and weight. I'm going to take the wiring harness off of the LIDAR sensor, just to have that separate. And, oh man, this wiring harness has some locking to it. Did I just break it trying to unplug it? Oh yeah, there's a lock on there that I totally did not notice and might have just broken. In other news, the ways I can destroy my LIDAR sensor. The connector still works, it's just not quite as grippy as it could be now. Anyway, there's my sensor after being abused in various ways. So one question to answer is kind of where to put things horizontally. So for some context, you can see right now I've got this bracket and some spacers such that I can mount the camera at a distance like that. And this was necessary for the center of gravity in this axis to be right. Let me get a better camera angle on all this. Oh yeah. Also in chat talking about other ways of getting a camera over long distances. This is something I have a little bit of experience with from this stream. Yeah, Wildmania says that they're currently using a USB webcam and has a limit due to the bad USB cables. Yeah, I had a similar issue with TucoCam. So my current wandering around cam for my cat is SDI, which has been helping a lot. Before that, I was using webcam with the longest cable that I could make work with it, which I think was like 16 feet or so, and it would sometimes spaz out and give me bad connections. This is definitely more reliable than that. There's also doodads that help you extend HDMI over long distances. It's just that those adapters are usually kind of expensive. And you know, if you want something that's designed for long distances to begin with, it's usually simpler and cheaper and more reliable to have SDI all the way around. The other thing you'll notice with HDMI, if you try to do complicated things with it, is that you can just start to have these it can start to take longer and be less reliable for devices to figure out what modes are supported and do the auto negotiation if your extenders and splitters and repeaters are also trying to do fancy things with the control signals in HDMI. Whereas with SDI, it's one way. So if you have an HDMI to SDI adapter, then that adapter is going to negotiate with your HDMI device about what mode to use, and then it's just going to pick something and start broadcasting it, and then the receiver has to deal with it. So that makes for just a single channel of high bandwidth data over coax. It's basically just optimized for sending over arbitrary cabling and routing setups. So that's why HDMI is mostly a consumer standard, whereas SDI is really popular. I mean, it was originally for broadcast. It's still used in broadcast as far as I know. And it's also recently started becoming more popular for surveillance cameras, since you can also just send pretty high quality video over long distances with cheap equipment. And yeah, if you're trying to build your own HDMI extenders, part of the problem there is it's just several signals that you have to manage. It's, you know, it's multiple twisted pairs for data, then it's a bunch of separate control channels. I mean, that's partly why HDMI cables are so thick, whereas SDI, it's literally just a single coaxial cable. So, oh neat, and Dawn is linking in chat a page that describes the difference between HDMI and SDI signals. Maybe we'll look at that really briefly. Hey Tuco, I hear you, little dude. Do I still have chat up? I guess I lost it. Oh yeah, this seems useful. Yeah, this seems like a great sort of summary. Yeah, basically you can run both of them over long distances. They're just have different different specs. Anyway, that might be useful. So yeah, this is nice because SDI was a good way of getting the cameras inexpensively and running it over a long distance. Oh, and Emily says apparently there's SDI fiber stuff too. Yeah, we talked about that last time, and yeah, Robert linked some stuff that seemed relatively cheap. I saw some stuff before that was super expensive, like over $1,000 for the converter. But this stuff was apparently a little less expensive, like $80 modules. But it looked like the transceiver had to plug into some other unit, and I don't know how expensive that unit is. All right, let's go to the camera. So yeah, I have this set up to mount. Let's see, how wide are these? I should actually measure these, because I am going to want to incorporate this balancing into the CAD model. Right now, I have a CAD model with obviously the part that I printed and a minimal mock-up of both this bracket here that it's attached to and the camera housing. But I don't really have much of the rest of this CAD modeled, so otherwise I would have noticed some of the interference problems earlier. So these two spacers, I'm gonna guess this is 8mm each. Maybe it's not. Oh, okay. These are a total of 12.6mm. They're each like 6.4mm. Something tells me these probably are not actually metric. Is this more even in imperial units? This looks like a 1/4 inch. Okay, so I have a 1/2 inch of spacing there. And so the first decision, I think, is whether the LIDAR goes on this side and I keep the camera pushed out even further, which would probably actually make my center of gravity situation kind of bad. Or I think the solution we're going to end up going with is we take these spacers off, the camera goes back to being close to here, which has the additional advantage of now the optical center is closer to the gimbal's actual center. So that's an improvement as far as camera mounting, but now it's very heavy on this side relative to the other. So then the question is, can I fix that by putting the LIDAR on this side? If it needs to go even further out, how much further? This looks like it also might kind of get in the way of the focus knob. A little bit in the way. You could also mount this on the bottom, perhaps, although that would negate the... Like, it's already pretty nicely balanced in this axis, so I don't want to mess with that if possible. So ideally, I want to find this center of gravity, which, where can I do that roughly with like a ruler? I just want like an edge to balance this on. Here's this, oh, here's a tool that I can balance it on maybe. So, more abuse. I think the center of gravity is... Sorry, little board. Oh, the filter came out again. I should probably put this back together while I do the CAD. I guess I just haven't decided whether I want the little mounting ears or not. Let's at least tape the board on like I had before. I think I over-eagerly took the tape off when it was really still useful. Oh, Robert says in chat, anyways, Azonenberg has convinced me that the best way to shove data into the PC at high speeds is to just slap an Ethernet frame header on it and put it over 10 gigabit Ethernet. I believe that. I have not personally done that myself, but I have personally said very similar things about USB in the past. But we've also established that I like USB possibly more than one actually should like USB. But yeah, once you start getting into those speeds, I mean, I'm sure that there's a lot more hardware you can find that speaks 10 gig Ethernet than USB 3. I mean, that might be changing. But until pretty recently, there haven't been many devices you can find that actually speak USB 3. So it looks like that's about the balance, kind of about between the URL and the email address on the label. So that doesn't have to be perfect, but it'll be nice for this to be roughly balanced in the motor rotation axis. So that would mean, oh, let's un-gimbal lock the gimbal. Here we go. That camera is really left heavy. That does not want to stay on there the way this is. That means, okay, so this would be, so for center of gravity reasons, as far as looking at forward back mounting, that actually wants to be pretty far forward. So like right about there is kind of where it wants to be, which is achievable. You know what this is looking like actually is maybe I don't even modify this bracket that I printed. Maybe I can just keep it and I add another thing to the right side. Possibly using this, there's another M2 screw on the right that was designed for like a little bracket for holding the camera, which is not super sturdy, but actually maybe that combined with the 3D printed thing that grips on the sides a little bit would be enough to hold this. So maybe the way I proceed is I 3D print a bracket that maybe gives me a little bit of spacing this way so that I can balance, use this as a counterweight with this spacing. And then in this axis lines things up so the center there is roughly centered in the motor. And then I think it would basically just be a little block that has a screw hole for this screw, then a piece that kind of wraps around the back of the LIDAR light sensor, and then something that screws onto the sensor. So then I think maybe the only other CAD design question I had is, will the mounting ears on this get in the way? So do I need to ditch the back cover of this, or can I keep that? Where's the back? There it is. Let's take the screws out for now. I do have to take my trusty little bit of Kapton tape off again. Oh, and also talking about PHYs and everything. Interesting. So Robert says that as far as he knows, the Xilinx FPGA transceivers can speak USB 3, but not USB 2. And that you'll need like a ULPI or whatever PHY for USB 2. And as far as they know, there's no open source HDL for doing USB. That's interesting. I sure thought I saw somebody's code for speaking USB over ULPI, but I could have been hallucinating that. It definitely seems like it'd be a nice open source core to have. Maybe that would be a fun project if I really want to get my hands super dirty with MySock, is to write a USB core in Python for it. Focus. Ears. Is one side of this actually heavier than the other? I should balance it in the other axis too. Maybe after I've put this case on, just so that I can avoid putting the tape on and pulling the tape off and doing that ad infinitum. Poor little LIDAR sensor. All the abuse. I mean, these ears aren't terrible, and I don't know that it would get in the way. But let's try some test movements. So, okay, just to verify the balance we had before, that was approximately, oops, just throw in the optics. That was approximately here. Let's see how much it changed with the back panel. Not much. That still seems to be pretty balanced right there. So then in this axis, it's pretty close. I was wondering whether the lenses were noticeably heavier on one side or the other, but it seems like they're pretty close that I can just center it and not worry too much. Okay, so now this might be the last test of the night. Let's put this here. Oh, would this be easier if I put like one M3 nut on here? I think it would. Just so the camera doesn't keep sliding around. Do I have an M3 nut handy, or do I have to go across the room for that? I think I need to go to the nut repository and check out some nuts. This isn't quite as disorganized a drawer as it looks. I have a lot of my screws sorted into different sizes such that the really large ones and or the ones I use frequently have their own drawer, but then the less common ones get lumped together so I don't have to spend as many drawers on things that I don't use frequently. This is a little bit of a tight spot since I'm using a long bolt here, but I think it'll fit. Oh, I can't believe I sent 12 volts into that LIDAR sensor. I'm glad it still works. I feel dumb for doing that, but everybody makes mistakes like that. That's what Sparky the blue spoke monster would say. I really like that critter. I think maybe we need to, well, so somebody suggested having Sparky iron-on patches, and we were having some other discussions about patches in general for the like flight suit, and then it also came up that, also I've got like the iron-on patch from Applied Science, Ben Krasnow's channel, and that's pretty cool. And you know, I'd like to offer some swag occasionally. And it'd be nice to have patches, perhaps, for people who like them. I might have to do a Twitter poll or something and see what kinds of swag people would end up actually liking. But stickers, patches, iron-on doodads, maybe t-shirts, those all seem like things that could happen. And I personally would love to have an iron-on patch with Sparky the blue spoke monster. Okay, so you can see the camera being super unbalanced right there. And then here's this again. Man, so the balance we wanted, it's pretty far this way. So if we want less than the width of the ears of counterweight spacing, then we will have to do without the ears and make our own back plate. But if we want this amount or more counterweight distance, then we can keep the ears. So how do I prototype this? It's tempting to just hot glue these things together with a spacer in between. I'm wondering if there's something even more prototypey I can do. Maybe one of these old 3D prints and some double-sided tape. I've got this double-sided tape, but I think we might need to use the stronger stuff I usually use for machining. Such a tiger. All right, this is Nido Permacell tape, which is pretty strong. I'm not going to use much of it, but I wanted something that will at least hold my test together. So first, I'm just going to take the LIDAR sensor and attach it to some arbitrary spacer that seems like it might be about right. Looking for trash in my desk that might be about the right size. I was going to use this printed block, but I think it's too small and too curved. This other one is probably also too small, but at least it's not curved, so maybe I could tape two of them together. Wow. Chuko, I hear what you're saying. I don't really understand it. Oh, actually, I understand what he wants. He wants to go outside, but it's way too late for that. I am not used to the new time change here. It's like after 1 a.m. here. It does not feel that late. I could probably say that with or without the daylight savings time, though. Chuko, it's kind of late for that, buddy. Let's actually remove the brim from this print. This is just getting in the way. These are pretty tough 3D prints. They're made out of that Tallman T-glass plastic. They just kind of rip instead of breaking brittly like PLA. I hear you, Cat, but it's not happening. Oh, Don is asking if anyone knows the model of the camera. I actually have this back plate over here which has the model info handy. Focus. There we go. Yeah, Crazy Fire HD 100p/SDI. I hear that these are discontinued, but you might still be able to find some. You can probably find some similar ones that are in possibly the same enclosure even if this particular model isn't going to be around that much longer. Oh yeah, Emily says speed names on USB are kind of messed up. What's the next one? Turbo speed, hyperspeed? Yeah, actually, like, so I'm fairly familiar with parts of the USB 3 spec since I worked on that at a day job a while ago, but I haven't really been keeping up with the more recent stuff like the 10 gigabit spec or power delivery. And so I don't know if they've given the 10 gigabit spec a new speed name beyond super speed, or whether they're just still calling it something uninformative, I guess. So let's zoom out a little bit. This is getting closer to what we're gonna have. Man, this thing is gonna look a little menacing in the air with its 3 lenses hovering around. It's also tempting to put a light on this thing since it is a hovering platform. That would actually be not a bad place to have a work light in the shop. And if it's going to have just some relatively beefy 12 or 24 volt power running to it, then yeah, I haven't decided whether, I mean, it makes the most sense, I think, to run 12 volt power to this since almost everything in it can just run directly off of 12 volts. But if I needed more power for any reason, then it might make sense to switch to a higher voltage for the actual distribution wiring. But luckily the robot motors are not on the platform, so it's just power for things like lighting and cameras and computing and bolt throwers, of course. Oh yeah, I forget who mentioned this. I think it was something that went by in chat when I was kind of half paying attention to it a while ago, and so I didn't quite see who said it, and I didn't have time to respond to it. But somebody was saying like a pneumatic tube-based bolt delivery system. And I don't know if this is going to be the same kind of a thought, but I'd been imagining that, yeah, if I wanted to have like a serious bolt thrower on here that could be remote controlled, that what if it just got the bolts through like, you know, like the 3D printers that have Bowden tube for feeding the plastic. What if in the harness of cabling it had a big pneumatic tube for bolts? That could be fun. Oh, Ryan is saying I should put some WS2812s on it. Yeah, maybe I should. Or maybe with something that's moving around, maybe even some of the APA 102s to get a higher update rate. So this is actually too thick. If you see this, this is now heavy on the LIDAR side. So let's try making it half that thickness and see how close that gets us to balancing. I guess that was the weak link. Oh, now the mounting ears are a problem again. I guess I need to take the back off yet again. Tim Williams in chat says, pro tip, if you want to force your USB 3.1 devices to lower speed mode, spread raspberry jam on the connectors before inserting them. That should work with any USB 3 or later devices that you want to force into high speed or lower mode, so like something lower than 3 gigabits, because the 3 gigabit and higher modes use new wiring. So the USB 3 compatible cables have 2 additional twisted pairs, which they're each half duplex high speed data, whereas the original twisted pair was half duplex, and they managed to get it to go up to 480 megabits, but that was all the hack they could hack. Did anybody else remember the short-lived optical USB 3 spec that was making the rounds? There was some image that was popular on like nerdy websites that showed some prototype USB cable that had the usual sort of USB plug, but if you imagine, let me grab one for an example here. Where is there not a USB cable within reach? What kind of lab is this? Here's the closest one, actually, right here. So that one looked like a normal USB plug, but, you know, whereas focus, is that just too close? I think that's too close. So yeah, I mean, if you look closely at a USB 3 cable, which this is not, but maybe I can get a USB 3 cable handy too. Yeah, here's a USB 3. So the blue is actually part of the standard. Like, I mean, that's just not like a fad. The standard was actually like, we need the customers to have a way of just differentiating them. So you can actually maybe see right away that there are, I mean, they're catching the light right now, so they're especially obvious. But those 4 additional connectors are the 2 super speed twisted pairs they added, and there we go. So you can kind of see that they're actually physically behind the connectors in front, and they make connection last. And if you don't get those connections, it assumes, even if both devices are super speed capable, it assumes the cable isn't, and so it gracefully downgrades. But yeah, the optical spec was weird. It was short-lived. I don't think they actually ever made very many of them. But it looked like this cable, except there were 2 little optical windows in the bottom here. It was super weird looking. And it must have been plastic optical fiber, but... Oh yeah, Ryan in chat says that they heard of the optical standard, but it died because no one would put the processing necessary for it in their mouse or dumb USB thing. I don't know if I buy that, because USB has always been about making the spec support different levels of adherence. So if you wanted a cheap device, it wouldn't have to support the super speed modes anyway. I think it must have been somebody complaining about either the cost or, you know, other infrastructure necessary for the super speed modes in particular. So, Oh, Dr. Toon in chat says that SATA cables are really cool. I agree. I haven't done this personally, but I've noticed a lot of like FPGA dev boards and I've seen like in teardowns like oscilloscopes, like just use SATA cables as interconnect for whatever they want because they're actually pretty nice cables. Yeah, that is true. They'd be a little thick for this particular application, but certainly fun. Okay, let's get this centered as best I can. Oh man, very little of that tape is actually sticking, but this might be enough to at least see if this balances. It is still a little LIDAR heavy, which is a good sign. That means I don't actually have to make this stick out very far for it to act as an effective counterweight. So that is just the thickness of an earlier version of our 3D printed bracket, and that's already still a little too thick. So I could probably calculate it at this point if I weighed things, but it might be easier and potentially a little more surefire to just find a thinner shim to put in there. Do I have a thinner shim? How thick is this shim to start with? So this piece is inches. 6 millimeters thick. So, well, okay, so I might call it a stopping point right now since I think I either need to find just like more shims to play with, which I don't have any handy, or to actually calculate it, which I don't feel like doing right now, it being late and me being lazy about it. But it looks like what we've established is that the distance necessary is less than 6 millimeters, but probably not by much, so maybe just like 4 or 5 millimeters. So I think what we need to do then is assume that this is not going to have a back piece, that we need to make the back piece part of the bracket because the ears get in the way. And then basically the next CAD piece then is leave this as it is. We don't need to mess with that bracket as far as I can tell. The one improvement I might make to it if we were going to reprint it is it'd be nice to be able to get the wires through it without breaking the bracket, so I might add a channel for the wires. Right now it's a through hole, so you have to pass the wires through the whole thing, which I thought at the time I needed to do for structural stability, but I think I think it's fine without that. So that bracket can probably stay as is, and then I would make another bracket that goes on the other side of this camera. I could have it attached via screws the same way, but I think that might be unnecessary. I think I might just use the little M2 since this is pretty lightweight. I don't need to hold a heavy thing. And then that bracket can probably even have a channel for this wire to go through so that the connector can go on this side, and then the bracket has like a little channel that routes the wire up and over, and then I can terminate it somewhere on this exposed circuit board back here. So I still need to open up the gimbal to, well, I need to extend out that 5-volt wire that I trimmed short in here so I can get it back out here since I need that again for the LIDAR. That's not a big deal. I also need to run that one extra wire for the I/O pin for the LIDAR through the gimbal. So that's going to be a little annoying, but I think I've got enough room. I think the gimbals all have a decent amount of free space in them right now, and one tiny little silicone wire isn't going to totally break everything. So I think that's the next step. I think this LIDAR is pretty promising, and this is going to make a great focus assistance for the robot. Because this is going to be the main, like, you know, I was talking before about there being a few different levels of control loop that handle different time scales and different levels of urgency. But this is basically the thing that is least urgent, but most interested in the result converging to a high degree. So like the other sensors, you know, obstacle avoidance, we don't really care how far away we are from the obstacle, but if we're getting close, we want to move away from it with pretty high urgency. Whereas this one, it's going to be lower priority, but having this LIDAR sensor like dialed into a particular distance is what's going to keep this camera in focus, and it's what's going to let us kind of glide over the shop at a relatively stable height away from everything. So this is going to be a really useful sensor. I'm happy that this is working out so far. So I think this is our wrap-up point for tonight. I'm still going through comments from chat because there's some interesting discussion going on here. Yeah, Dr. Toon says 10 gig over Cat6 is quite a feat of engineering. I agree. I don't know that much about 10 gig Ethernet from, because I'm more familiar with well, I barely even know much about 1 gig Ethernet. I've only really actually worked at a really low level with 10 base T, and I've read documentation about how 100 base T works and looked at it on the oscilloscope, and I kind of vaguely understand how gigabit works, but yeah, I haven't actually looked at the spec for 10 gigabit over copper. That seems pretty interesting. Oh, what is this we're talking about on Amazon being in stock in April? How much beer do I have left? I have almost no beer left. Wow. Oh, I heard about these. Haven't these been vaporware for a long time? I forget whether I was hearing about these like a long time ago when I was writing USB 3 virtualization code, or whether it was more recent when we were trying to extend the Connect sensor over long distances. But yeah, that's interesting. They're really expensive. Maybe a little less than I would have expected, but still, wow. Oh, is this recommending like Connect related stuff? Oh yeah, recommended Connect adapter, yeah, because that's like one of the problems that you run into in computer art installations is that if you want to use a Connect sensor, great, you better hope that the sensor is really close to your computer. Hey, Tuke. Oh yeah. That reminds me of a related question. So, Kyle, who's been very generous, sent me this box of goodies today, including this Asus depth camera. I'm curious how much computer is required to drive this, whether I need a USB 3 port, whether I need a GPU, because that'll inform whether I'm running this off of like a Raspberry Pi 3 or some other small single board computer with USB or something a little beefier. Oh, so it's OpenNI compatible. Is this saying USB 2 and 3? I mean, I could plug it into the computer and see what it reports as. Maybe that's the fastest thing to do and most surefire. Camera plugged into a USB 3 capable hub. What do we got? This is PrimeSense device. It is attached through the USB 2 path, which seems like a good sign. So this might just need high-speed USB, which a Raspberry Pi can handle just fine. I'm going to have to look into this protocol some more when it isn't quite so late, but this is a good first start. Because if you look at the Connect side, so the original Connect is giant and power hungry, but does most of the processing on board, so it gives you basically a USB 2 isochronous stream with depth and RGB images. Whereas the Connect V2, if I remember right, it does, let me try it. I actually looked at this code a while ago because there's actually a bunch of processing you need to do on the GPU, and there are some open source drivers for the Connect V2 that include like OpenCL code to do this, or CUDA code, I think. I forget exactly what the calculation is, but I think it's basically like a filtering operation that maps the raw time of flight data back into a usable depth map, and the Connect V2 doesn't do that in hardware, so you've got to do it on an actual GPU. So there's still an open question of whether this saves enough work for the computer that the computer is going to need a GPU, in which case maybe the Raspberry Pi won't cut it. But assuming this sends me cooked enough data over USB, then Raspberry Pi is probably going to be all right. So we'll save that for a future investigation, since I don't really have the time to give this proper treatment right now, but it will be interesting. If this works out, then the way I imagine this working is that, you know, if we go back to our stick figure drawing of the cat camera here, let's put this cover somewhere where I'm not going to lose all the fasteners. So if we go to our kind of cartoon drawing of this cat camera, so we've got the opportunity to place sensors in 3 different places. We've got the gimbal itself, which is pointing at whatever the camera is actually looking at, but is difficult to mount things on, as we've been struggling with just now. There's the actual body of the robot, which could have additional like motors or gimbals on it if we wanted, but probably best to keep that simple unless we needed to make it more complicated. And then there's just elsewhere in the room, potentially stationary or on a separate gimbal. So there's also, like, if I was going to draw more of this, you know, there's basically like a mezzanine level over here, which is like where I sleep. And I could put a camera over here that aims down and can see the space. That might be what I do with the IR, the temperature camera for locating the cat. The depth camera, I can just imagine it being super useful for a number of reasons to have a depth camera on the robot. I could use that for like location and mapping. So SLAM, simultaneous location and mapping, is like a thing that I could just like apply to this and get a position and a 3D map of the environment. There are various algorithms that do that. Maybe overkill for this situation, but it might also be nice just to have the ability to have a 3D image of whatever is under the robot. And it is going to be bouncing around a bit unless I mount that on another gimbal. But either I correct that in software or I use another gimbal. I think software might be easier in this case. But so I think my plan is going to be this platform has some electronics on it, Raspberry Pi, you know, the interface between it and the gimbal controller, the SDI repeater, and then facing downward, so kind of like a cone like that or so, maybe more symmetric than that, depending on how much I need to avoid the gimbal. That would be my depth camera. Imagine like if we looked at this from the bottom, that, so this is part of why I'm thinking about the difference between, so we looked a little bit earlier at the like kind of professional like sports ball cameras that do this, and it seemed to have a design that was kind of more like, you know, wires coming in at the top, then like a little hub, and then a pole, and then it looked like they had like a counterweight in the middle, and then another like gimbal contraption that actually holds the camera. That, from my brief look at the sports ball footage we were looking at earlier today, that's kind of how this worked. And then Emily in chat is just suggesting to chip the cat and triangulate with RF. I don't think that would work at the distances we're interested in, at least not with the kinds of RF power I would want to emit continuously. I think the best long-term or long-distance cat tracking is probably a combination of sound and FLIR heat camera from a far distance. So this was the kind of sports ball scenario, but I think what I'm going to end up with something a bit more like wide-based like this, where the wires come in like that, and then the gimbal is more mounted like close in like that. And then this would give me room to have, you know, my other camera pointing down this way. But this means that, you know, this has to be far enough away that way that this cone doesn't just end up looking at this camera, and it has to be far enough up this way. So like ideally I actually embed this in the robot and just have the lenses pointing down, and then have this far enough away that this cone doesn't just aim directly at the gimbal, and then the gimbal has free unobstructed vision in all directions. Oh, Don says that in this the counterweight is on top for center of gravity. Oh, that's right. Yeah, that makes more sense. Because yeah, otherwise it's going to act like a pendulum as you move it around. That's right. So then counterweight on top. That makes more sense. So you're just moving it around by its center of gravity, which shouldn't introduce any additional torque. So I could imagine doing that for this. That would also mean, if it's useful, there's another anchoring point up here to anchor the bungee wire to, and then the wire could kind of go down here without a lot of disturbing. This doesn't give maybe quite enough as much room to mount the electronics, but I mean the electronics package can be up here. That's probably fine. Okay, interesting. Oh, now I'm catching up on chat. Maybe let's share that with the class. Oh, okay, so Don's saying don't connect anything to the counterweight because that changes the center of gravity. Yeah, that's probably right. Cables are turning right through the center of gravity of the gimbal. Oh, tunneling right through the center of gravity of the gimbal. Interesting. Wildmania suggests pressure sensors on the floor for TUCO. I don't know about like a lot of pressure sensors because that seems difficult to cover the area, but I have considered basically contact microphones, so taking piezo transducers and gluing them to the floor at various points around the edges, and then I could use that to maybe roughly triangulate vibrations on the floor as he's walking around. So that might be interesting. Yeah, I think you guys are right. The wire needs to be attached at the same point as the ropes. Yeah. Is it going to have a third axis movement? Oh, so I've only been drawing 2 wires because this is just kind of a side view, but I'd actually been imagining this from the top as looking like a square with, you know, if you imagine the center of gravity is here, and then I have basically lines through here where you can imagine the force is going through the plastic here, and then the cord is anchored to the side, and then the cord goes off to the pulley. And then I have all this area to mount electronics. That's kind of what I'd been originally thinking of. But I guess I don't totally see the problem with this. I mean, I guess one problem is, as this moves, for example, along this axis, then the angle between this and that pulley changes. So then even if you have this lined up where everything is straight through to the center of gravity when it's in the middle of the room, then it travels to the side of the room, and now all of a sudden pulling on this motor ends up torquing it around. So I think that's the problem we're trying to deal with. Wildmania says that seismic detection won't work on a cat because they walk quietly. Have you met Tuco? I mean, he walks quietly when he wants to, but when he's chasing a bolt, I think that might trigger the sensors. And I think specifically the bolt bouncing around on the ground is what I think I might have the best chance of discovering. So yeah, this is some good feedback. So yeah, this might work, but it also seems like if the angles aren't totally right, then pulling on these wires would end up causing a lot of like rotational torque around here that would destabilize it. So yeah, if I went with something more like this, with a counterweight, then just this at the center of gravity in all three axes as best as I can. If I do it this way, then I might see what I can do about putting the electronics up here. So like the Raspberry Pi or whatever computer up here, there aren't a lot of electronics on here. There's a Raspberry Pi, there's a board that gives me PWM outputs to drive the gimbal controller. There's the SDI amplifier, which actually still needs to be right next to the gimbal, so I can't really move that up easily. The other problem with this, though, is that it doesn't give me a good place to put downward-facing sensors, which I wanted to have. So like this seems like it might be likely to have torques that I'm not into, but it gives me a lot of room for mounting additional sensor packages and additional like Tuco toys pointing up and down. Whereas this, I think this would be really hard to design add-ons for. But I'll think about this. I think I probably have to wrap up this stream, but there's definitely some stuff to think about here. Yeah, tracking this clever cat is definitely hard. We've talked about this a few times before, the collar with an IR beacon. Tuco doesn't always wear a collar, but I could certainly have him wear a collar during the streams, and that would make it easier for that to work out. Yeah, tracking a clever tiger is hard. Yeah, I think the easiest tracking solution to actually make reliable, given such a clever tiger is going to be the thermal vision. And I guess one way I imagine that working is if I can put the thermal camera high up enough that it gets a view of most of the shop without having to pan around, then I can basically do background subtraction. So look for motion. Anything that changes slowly is just the environment being hot or warming up as the sun moves around. And then, oh, that's interesting. Yeah, you can still attach a large square above the cam below the mount points. Yeah, I guess I could do that. I'm not, like, just thinking about the physics of this in my mind, I have a hard time imagining that being as stable as just having this thing be overall less tall. Because this strategy with the, the top part and the bottom part and the mounting in the middle, that just seems like if I'm going to actually give them a lot of separation like that. I guess I just imagine that strategy is probably useful when you're moving around a really heavy camera, but since my camera is so light, I don't know if that's going to be as relevant. Now I'm trying to parse this comment from Don. On the Skycam, there's a free-floating gimbal at the CG. Yeah, I get that. And I mean, like, I'm sure that the fancy version of this has all of the centers of gravity lined up really nicely, whereas I'm kind of doing whatever I can with the parts available. So as this moves around, you would get some shifting in the image, since, like, for example, the stabilizer itself doesn't have the optical centers lined up just right. But I think given the speeds I'm going to be moving this at, it might not be good at tracking the ultimate fast sports balls, but I think it'll be fine for the cat, especially given that I'm going to have it somewhat high up and just panning around for the most part. But this is good to keep in mind. I want this to work as well as I can, make it work reasonably well, or reasonably. But Yeah, I don't like the idea of making it super tall. I like the idea of keeping it fairly flat. I mean, there are two things that are maybe different between my setup and the kind of Skycam thing, is that my whole setup is much lighter, so I'm not moving around a really heavy camera. Oh, that's interesting. That compensates for the twisting. Oh, yeah, well, so that's the other thing is, so if we're concerned about this twisting in this axis due to, that thing where, okay, so I guess we're saying that there are a couple of solutions to that. Either attach it directly to the pole, but for that strategy to work, we have to kind of split it like this, so we have something above and something below. Or I'm thinking keep it attached at the corners, but just try to compensate for that as much as possible with the gimbal, which was my strategy thus far. My strategy so far was to assume that I can't necessarily control the position or like the orientation of this especially well, but that I use the gimbal. I think Don and I are maybe just slightly talking past each other. Because I was trying to determine whether there's any reason to go with this design that we were seeing on the professional cameras or this one, which is just kind of the intuitive design that I've been planning on implementing. And so, my plan was to have this such that for most of the travel, these are not torquing the platform much as I pull it around. As you get to the edges, that gets more like a problem. But for the camera, I'm compensating that pretty much entirely with the gimbal, I hope. For other things on here that are not mounted on the gimbal, I think that's really the difference here, is like this strategy has very little room for anything that is not on the gimbal. I can put something down here, but that just means that my counterweight has to now be even heavier, which just makes the problem even worse. So I don't think I like that. Or I put the stuff up here, in which case now it's looking through these wires, which is not good for sensors. Oh, Alfie's asking if they can make a suggestion. Sure, of course. Just go right ahead. Don't have to ask permission. So then, I'm thinking that this strategy means that the extra height doesn't have to be a thing. I can attach it at the corners. It's not necessarily going to be the best geometry, but it avoids this problem. And now I have a good spot to mount these extra sensors without obstruction. This is also just easy to make. I think this can either be a couple of reasonably sized 3D prints or a piece of sheet material that I attach some brackets to. Oh, I see. Don is mentioning that the Skycam doesn't have an active gimbal. Ah, that was a big difference I was not aware of. I see. And then if it's up in the air, I might as well have an RGB laser and mirror for parties. I guess I could do that. Actually, I've been really into laser projectors. That was one of those things that I made a really, really basic kind of laser spirograph thing as a kid with motors, like DC motors, and I made a nicer version of that much later with hard disk voice coils, and I made an even better version, still with hard disk voice coils, but with an actual better control loop involved. And it'd be interesting to take that a step further and actually make a proper laser projector there. Corners of your mounting plate aren't rigidly mounted. You can hang stuff below it without a counterweight and it'll stay stable. Do you mean... I think we're on the same page. I think this is pretty much something I've already been assuming, but let me see if we're on the same page. So I guess you're saying that because these corners are under some tension, then I can just basically hang a rigid structure down here that has some sensor on it and it won't wobble around too much. I think that's largely okay. I can imagine, I forget where I've seen this, but I think I saw another structure that basically, if you can imagine a tetrahedral frame, like that, but with hidden line removal maybe. And imagine this vertex has your camera, and then you have cables on these vertices. I thought I saw something like this that had, And like, I like this geometry because basically this gives you a nice long lever such that the tension between these two cables has a decent amount of mechanical advantage for anchoring this point rigidly. So I think that's what we're talking about. Whoa, neat. You can get a 1 watt RGB with 20K pulse per second galvos, I assume that means, for $400. That's amazing. I might have to try something like that. Although, the other thing is the laser doesn't necessarily need to go on this moving robot. I think that would get enough deflection that I could probably just mount it somewhere stationary and don't need to get it involved with this project necessarily. But that's a neat idea too, like cat avoidance laser. The other thing is, like, the laser doesn't have to be mounted on this robot for it to interact with the robot. The laser could just be mounted on the ceiling somewhere out of the way and then kind of roughly calibrate its projection to the floor that this robot is seeing, and then have some way that, you know, you could interact with. I mean, there's like a whole host of interactions we could have with this camera over the internet based on clicking on things on the screen and having lasers or bolts emerge at that location, depending on how calibrated this could be. That could be super fun. Anyway, this has been a super fun stream, but I think I need to wrap it up so that I can get to bed at some point this week. But more of this soon. I hope I have some time to work on this. Well, I should have plenty of time to work on this weekend, because I'm really anxious to actually get the gimbal part finished. Here we have our currently very off-balance camera, which needs the small hardware again, but I'm pretty happy with this setup. Oh, this was off screen before, but this was the SDI cable I was using with this sequence of little adapters to get it down to. This is BNC to SMA, and then this is my SMA adapter I made on a previous stream that's just, well, it's not an adapter, it's a termination, but it's this tiny 0.81 millimeter coax terminated into SMA using kind of a hack. Oh yeah, so I think Alfie and I are on the same page. They're saying as long as the mounting surface is a little wider than the suspension distance, you should be stable. Yeah, I think we're on the same page. I don't know exactly what it's going to be shaped like, but I think we've got the general setup going. Oh, small world, Markan. Yeah, I saw his laser setup, not in person, but on Twitter ages ago, and I know he's been bringing it to CCC for a while. He and I still have not met in person, but we used to do like video game hackery related stuff together on IRC, so it'd be nice to actually meet in person sometime. Tuco definitely goes after lasers. I don't think he likes them as much as the bolts, but they definitely are a thing. All right. I could keep going with this all night, but I probably shouldn't. I don't think Tuco is on frame right now. So I think we'll just finish up with the slides as is tradition. Oh, thanks for joining. Thanks for sticking around late, if it's late where you are. Thanks for joining regardless, and happy hacking, everyone. I'll see you all next time.